Hi everyone, Jesse Brockwell from Capstone Academics here. Thanks so much for joining, and this is just a quick intro to get you guys familiarized with exactly how these videos should be used. All these videos are walkthroughs for the problems in the College Board official SAT study guide. Most people are going to find it best to try and work through a section in the book themselves and then check their answers. Then watch these videos to help them understand any problems they answered incorrectly or didn't answer at all. This is really how these videos are meant to be used, but I highly recommend that you actually watch these videos all the way through, especially if there are any problems that you had to guess or hack at in order to get it right. If you've got that nagging feeling that a problem could have been done more efficiently, then chances are a better approach is actually covered in the videos. So, for best results, just watch the videos all the way through or carefully skip around if you like. If you're doing this for the reading or writing and language sections in particular though, be sure to make sure you actually read through the entire passage because all these explanations are given under the assumption that you have read these passages already. But again, you're probably better off just working through the whole section yourself ahead of time, that way you can at least give it a shot on your own first. So, with introductions out of the way, let's get started.
Okay guys, here we go with SAT practice test number 1, the no calc math. We're on the first one. First one's always an easy, so make sure not to overthink it. First thing you can do is just plug in that 3 for k right here. Multiply both sides by 3. X minus 1 is 9. Add the 1 over. And x is 10. Easy as that. Usually it's best to approach these algebraically just because sometimes these equations will be kind of too hard for you to just go ahead and plug all the answers in, or too time consuming to do so. But if you choose to with one this easy, that's totally fine. Just make sure you're not wasting too much time. So if you go in over here and you're like, okay, what number minus 1 divided by 3 ends up equaling 3? You're like, okay, well 9 divided by 3 is 3, so that number must be 10. So that's the other way you can do this quickly. Okay guys, so for this one you actually don't even need to know that I is the square root of negative 1, because this is just combining like terms. So all you need to do is just drop the parentheses and combine like terms. So 7 plus negative 8 is negative 1. 3i plus 9i is positive 12i. And that is it. So for some of the tougher problems, you'll need to know that I squared is negative 1, just for problems that involve foiling. But that is it. Alright, so number 3. Armand sent M text messages each hour for 5 hours. So his total number of text messages is just 5M. Tyrone sent P messages per hour, so his total number is 4P. And their total is just those added. That is all. Alright, number 4 is actually super important because it actually illustrates the most popular problem type on the entire SAT math section, and that is slope-intercept form word problems. So if you guys remember from 8th grade and beyond, slope-intercept form is just y equals mx plus b. This is your slope, but in word problems it's going to be your rate of increase or decrease. Your b, or your y-intercept, is always your initial amount or a flat fee. So like let's say you were renting a car and they were going to charge you $100 straight up, but plus $50 every day. The $100 would be the flat fee that you pay anyway, despite the daily cost. Okay. So, for example, let's take an exotic animal that we would want a lot of. So, I'm partial to the platypus. I think it's a pretty fantastic animal. So, let's say you start with 4 platypi and gain 2 every week. So if you think about the way you'd code that into an equation, your total number of platypi would just be the 4 that you start with plus 2 every week. I'll be SAT obnoxious and just code 2 every week as 2w, right? Now watch what happens when I flip the variables around, or flip the terms around rather, and then change the variables over to y and x. All of a sudden we have something that's in slope-intercept form. If you were to graph this, total platypi would go here, And this is your total weeks that have gone by on your x-axis. Now, if you remember, the way you graph in slope-intercept form is you always just start here on the y-axis with 4, which makes sense because it's your initial amount, right? And then from here, you just go up 2 over to the right 1. But I'm going to tweak something here. Instead of gaining 2 every week, what if we gained 2 every 3 weeks? How would that affect things? Well, it actually means that your slope would become 2/3. And this actually makes sense because you'd be going up 2 platypi, but it would take 3 weeks this time. So if you put that on the graph, you would have 6 platypi after 3 weeks. So up 2 over 3. Go up 2 over 3 again for another point. And you've got your line. You only need 2 points, but just to reiterate the way slope works, right? In case you need a little reminder from 8th grade. And up here we have 8. And that took 6 weeks. So just a little reminder in terms of the way the actual points would look as full coordinates. This would be 0, 4, which means after 0 weeks you have 4 platypi, which makes sense because that's how many you started with, right? And then after 3 weeks you have 6. And after 6 weeks you have 8. So guys, this is actually the most popular problem type on the entire test. They want you to be able to look at a graph like this and know that this is the equation that represents it. Or, more commonly actually, that the disguised form of the equation would look like that, with different variables and with the terms turned around, things like that. So, just to prove it, we'll look at this one. Most people look at this problem commonsensically. They're like, okay, P means the number of phones left. And then you notice that the first number is 108. So, like, okay, her number of phones left is 108 minus 23 times the number of days she's been working. So 108 would definitely represent her initial amount of phones, and that would be correct. But you'll want to be able to look at these problems through this lens. Very, very important, because you'll see this constantly. Reorder the terms. Change it over to y and x. And if you interpret this according to this, then your 108 becomes your initial amount, which is what she's starting with each week. Now, if they had asked what the negative 23 meant, that would be her rate of fixing phones. So her number of phones left goes down 23 phones every 1 day. There's another problem exactly like this 2 problems later on number 6, which we'll get to very shortly. Okay, for number 5, guys, don't be intimidated by all these crazy looking terms. Just try not to get too dyslexic about the variable order and all that kind of stuff. So what may help is actually draw in a little -1 here. I highly, highly recommend that you actually show the results of distributing this negative, or the -1, whichever you're used to using, before you try and combine like terms. Okay, it's just too much to juggle all those negatives in your head and all your negative rules and all that kind of stuff. So this is plus x squared y minus 3xy squared plus 3y squared. Now you can use this little strategy of like boxing in like terms for your first type. So is there another x squared y term here? Yes, there is. It's right here. So box that in. And then I would make sure to use a different type of way of noting that this is a like term, because it's a different type of like term. So I'll use a circle for the y squared terms, which there's another one right here. And then I'm going to use an underline, which is yet another type for the xy squared terms. So when you combine these two guys, that's basically, I'll use some green here, 1x squared y plus another x squared y makes 2x squared y's. And then if you look at the y squareds, these are actually going to cancel each other out. So these are gone. And then when you combine the 5xy squared and the negative 3xy squared, that's positive 2xy squared, which is C. So again, looks a lot worse than it is. Just be really, really careful with showing your work and combining like terms. Don't make any silly mistakes, because remember, these easies are worth just as much as the hards are. All right, number 6. So guys, remember, if you have an equation that has 2 variables in it, both to the first power, that's basically slope-intercept form in disguise. So if it helps, you can rewrite the h and the a as just y and x, and then be sure to interpret this through the lens of the slope-intercept form word problem structure that we talked about before, where this number on the x is just your slope, or in the case of a word problem, your rate of increase or decrease, whereas the number at the end is always your initial amount or your flat fee. So they're basically saying this model represents the height of a boy in inches between the age of 2 and 5, where a is their age in years, right? And they're basically saying, like, what's the increase in height each year? Watch out for words like each and every and per, because they indicate rates, and that tells you that it's actually asking about slope specifically. So if you look at the slope here, it's just going to be 3 over 1, which in context of this problem just means 3 inches every 1 year. So you actually don't even have to do any math. It's just a. So you can see how immensely helpful this is. Again, the most popular problem type on the entire test is interpreting slope-intercept form word problems that are somewhat in disguise because they use different variables or they reorder the terms, or both. So keep an eye out for that. Number 7. So guys, keep in mind you're really not going to see anything that's this difficult moving forward here. This is a pretty old test, and we have, as you can see, m equals huge confusing fraction times p. Again, they don't really do this much anymore. I mean, they could have what are called literal equations, where you have y equals dxn plus 4mp, and then they want you to solve for m, right? That's a literal equation. But they're not really going to give you stuff that's this complicated on the test much anymore. Again, this is a really old test, so don't worry too much about this, but just for practice sake, right? All you really have to do here is imagine that fraction is less complicated. So I'll use just like 3/5 to maintain the structure of the fraction, right? Just so I can figure out how I'd isolate p, because as you can see by all these answers here, all they're doing is isolating p. So I'm maintaining the structure of the fraction. I basically have a numerator and I basically have a denominator. So you just ask yourself, like, okay, how do I get that p by itself? And when you have a fraction linked by multiplication, you just multiply both sides by the reciprocal of that fraction. And these will cross-cancel each other, like that. And then if I just put the p on the left so it looks like all the other answers, you'll notice that p equals just the flipped version of the fraction, or the reciprocal, times m. So you just pick the option that's the flipped version of this times m, and that is b. Number 8 is especially important. Now, the reason for this is there are 3 different methods that you can use, at least, to approach number 8, and all 3 of them are actually pretty important. Now, the first one I'll go over is typically people's first instinct, and that is just plugging in. Now, you don't want to use plugging in random numbers as an initial approach to a problem, because if you're preparing for the SAT, it is a very intelligent test. It's a very old and vetted test, right? And the best way to improve on the math is to actually get better at the math, okay? And you're not going to get better at the math by just plugging in numbers whenever you whimsically want to, right? It's better for you to actually learn the math and be able to do things algebraically than just sort of hacking at all the problems and just hoping for the best, right? So I'll show you guys the plugging in method, but just keep in mind that it's supposed to be sort of a last resort approach, okay? Now, with that in mind, you might be like, okay, so a divided by b is 2. So let's just figure out 2 numbers that divide to equal 2. So a lot of people choose a to be 4 and b to be 2, which is totally fine. Now, you get away with this because you get away with plugging in because if you pick 2 numbers that divide to get 2, it's a ratio. Whereas in other situations, if they tell you that 2 numbers add up to be 6, they could be a couple different things, right? They could be 4 and 2, or they could be 3 and 3. And a lot of times there's another restriction present in addition to what you're seeing right here. So by choosing, let's say, 4 and 2 or 3 and 3, you may be violating another restriction in the problem. So that's why plugging in isn't always a safe method, okay? So with all that said, it's okay here because any 2 numbers you pick that divide to be 2 will be in a ratio of 2 to 1, so it'll all work out. But in any case, we chose a is 4, b is 2. So when you divide them, you get 2. You're good to go. And then they're wondering what 4b over a is. So you just plug in your a and your b values. So like 4 times 2 over 4, that's 8 over 4, which is 2. So there we go. that's the first method. Second method. This is probably the most reliable. Substitution. Substitution will always work. Now, you can tell that you can substitute here because you have two equations with two different variables. Now, if you ask yourself which one of these is easier to solve for, the a or the b, it would definitely be the a, just because you can multiply both sides by b, and just get a is 2b. Take the 2b and plug it in for this a now, and you just end up getting 4b over 2b. The b's cancel, and you get 2. Easy peasy. Now, the last one. This is pretty much the way this was meant to be solved. Manipulating equations. You may have noticed that a over b has a really similar structure to 4b over a. You just kind of have to mess with it a little bit. So like, okay, if we have a over b is 2, but we're trying to get to a position where it's like b over a, you could just flip this, call this 2 over 1, and just flip both sides of the fraction there. So you actually end up getting b over a equals 1 over 2. Now this is algebraically legal because it's basically like raising both sides to the negative first power, which is just flipping. But needless to say, it's algebraically legal, so this is totally fine. Now remember, you're trying to get to 4b over a. That's what you're trying to turn this side into. So what would you need to do that? Just a 4. So multiply both sides by 4. Because you did it to both sides, it's totally fine. So there's your 2. Another example of this might be this. Looks a lot harder than it is, but just ask yourself, how would you get what you started with up to this? Or how would you start to make it look like that? And what you can do is just double both sides. And you'll have your 6x plus 4y piece. Now, if you ask yourself what the only thing missing is, you'd say, okay, just the minus 5. So subtract 5 from both sides. And you'll actually create what they wanted. We'll see more examples of this moving forward, but super, super important strategy, guys. Okay, so number 9. So number 9 is illustrating probably the most popular problem type on the math portion of the SAT other than slope-intercept form word problems, and it's systems of equations, particularly elimination. So when you have both equations in the format ax plus by equals c, that's ideally set up for elimination. I'm just going to sort of provide my own explanation here, my own example of how to do elimination easily. So I'm just going to use my own example to sort of demonstrate how you eliminate. And I'm just going to have the first one be 5x plus 2y equals 10. Second one's going to be 7x plus 3y equals 11. Now, basically what you're doing is you're asking yourself which variable would be easier to have meet up at a number and then cancel when you add the two equations. So if you look at the 5x and the 7x, you want to think about this like common denominators, like where do 5 and 7 meet up for common denominators? And that would be at 35. So pretty big number, might not be our best bet. So we look over at the y's here, and where do 2 and 3 meet up? And that would be at 6. So definitely a lot easier to have the y's meet up at 6 and then add and cancel than have the x's meet up at 35. So what do we need to multiply the top equation by to get the 2y up to a 6y? That would just be 3. And make sure you distribute that to all these here. And then what would you need to multiply the bottom by to get the 3y up to a negative 6y? And that would just be negative 2. Now I'm just going to write the results here. Got 15x plus 6y equals 30. Negative 14x, negative 6y, negative 22. And then when you add these, 15x minus 14x is just 1x. The y's cancel, and then you just get 8. So that's your first variable right there. Now you just got to plug this back into, ideally, the easier of the two equations, which would be the top one, just because of the lower multiplier with this 5 right here. So we're going to go ahead and do the top one. So 5 times 8 plus 2y equals 10. And then 40. Subtract the 40. negative 30. Divide both sides by 2. Y is negative 15. So usually the solution to a system like this is expressed as a point. And the reason for that is these are actually two lines that are graphed on the same graph, and they're meeting up at the point with coordinates 8, negative 15 in this case. So that's what your solution is to a system. It's the point where the two lines intersect. So more on that later. But looking back here now, if you notice, these terms aren't lining up the way they should. We have like a 3x and a 2y here, where it should be x and x in the first spots. And then here we've got a y and an x, and it should be both y's there. So it's really this bottom equation that's out of order. So let's go ahead and swap those two terms. So I'm just going to rewrite the top here. And then swapping the two terms on the bottom looks like this. And then you can ask yourself, like, okay, should I have the x's meet up at 3 or the y's meet up at 4? Now, there's not a big difference in difficulty here, obviously, but if you're trying to keep your numbers as low as possible in terms of like what you're multiplying by, because this is a no calculator section, right? You'd probably prefer to multiply the bottom by negative 2, because if not, you'd be doing the bottom by 3, and that would just make your 19 times 3 a little bit bigger than it needs to be. So bottom by negative 2, distribute that in, and I'm just going to rewrite the top. It's a nice way to stay organized. And then writing the results on the bottom here, positive 2x, negative 4y, positive 38. Add the two equations, 5x, y's cancel, 15. Divide both sides by 5. So x is 3. Now in this case you can actually stop here, because if you look at all these x options in the answers, only one of those is 3. So you can just automatically pick B. Now in some cases they'll have multiple options in the answers that have x coordinates of 3. And in that case you would actually have to go back in and plug in x to get your y. And we'll go ahead and do that now. I'll just use my bottom equation here. And I'm talking about this one right here. I'm just going to use that. So plugging the x in, it's negative x, so negative 3 plus 2y equals negative 19. Then you could add the 3. 2y equals negative 16. And then just dividing both sides by 2. Y is negative 8. So again, get used to expressing the solution to a system as the point where the two lines intersect. So 3, negative 8, and you can see that that's B there. Again, this is the most popular problem type, along with slope-intercept word problems that you'll see on the entirety of the math portion of the SAT. Proof of that is actually later in this section. Number 18 is actually another system of equations that's set up for elimination. So 2 questions out of a 20-question set that are exactly the same type. It's, there it is. So guys, a lot of you will prefer one method of solving systems to another pretty strongly. So some people just say like, oh, substitution's so much easier for me, or oh, elimination's so much easier for me. And then they'll kind of refuse to do the other method ever. But you really, really want to become comfortable with both, just because both of these methods have their applications in many different problems in this test. It's both concepts are just very, very heavily well represented on the test. So get comfortable with both and you'll be... Okay guys, so number 10. First thing we want to do is just hone in on this right here, the fact that g of 4 equals 8. So remember, whenever they replace the number that's right here with something else, you're just going to want to plug it in for all the x's that you see in the equation. That's just the essence of function notation. So it'll just look like this. Like if regular g of x is just ax squared plus 24, g of 4 is just going to be a times 4 squared plus 24. And then you can simplify this a little bit here. So you get 16a plus 24. But then because they told you g of 4 equals 8, you could also write that out. Now since both of these things equal the g of 4, it must mean that 16a plus 24 equals 8. And this is going to allow you to solve for a. So just crank it out, negative 16. And you end up with a is negative 1. Now that you have what a is, you can actually plug it back into the equation so you can get the full equation without any other, extra variables in there. So it's actually this, and now that you have the equation without a in there, you can just figure out what g of negative 4 is by plugging it in. So it should look like this. and then you get negative. This is positive 16, so it's like -1 times positive 16. So you end up with negative 16 plus 24. And you'll end up getting positive 8 for this. Now, a lot of people sort of see through having to do all this work because there is a shortcut to this. So notice how you are squaring whatever number you put in there. So if you put in positive 4 and you get 8, if you put in negative 4, well, because it's squared, it's going to turn into positive 16 anyway. So you're going to end up with the same result. You could sort of shortcut it like that and just get 8 that way if you're looking to save some time. But as a general practice, it's better to find the value of any missing variables so you can get the full equation like we did here. It's just better in general. Okay, so there it is. All right, so with number 11, they're asking what's the price of beef when it's equal to the price per pound of chicken? And B just represents the price of the beef, and then C is the price of the chicken. So since they're wondering when they're equal, you can literally just take this stuff and set that equal. So, I mean, the toughest part about this is just managing your decimals if it's been a while since you've done work with decimals, like adding, subtracting, and eventually we'll be dividing here. So I'll show you a little way around that, which is really nice. But for now, you just sort of solve this algebraically. They want to know when the prices are equal, so you set those prices equal and just solve for x. Now, if you're trying to avoid negatives, just bring the 0.25x over to the right side. So the way you can view this is like 40 cents minus 25 cents. That's kind of the easiest way for most people. So you just get 0.15x for this, and then just bring down your $1.75 and your $2.35. And then you'll need to bring this $1.75 over to the left. And then $2.35 minus $1.75, 60 cents. Remember, this is a no calc section, so it's important to use whatever you can to make things easier for yourself. So this is the challenging part for most people. You have to divide both sides by 0.15. So when you do that, there's a really nice trick for this. So basically, like, a lot of people will recognize that this is 4 right away, which is great, like awesome. But if you're having trouble, this can really help. If you want to get decimals out of fractions, you can just move the decimals an equal number of places, top and bottom, over to the right so that all the numbers become whole. So here we only need to move each one 2 places. That's all we need to do. But basically, this will end up making it x equals 60 over 15. And then when you reduce that, or just divide it out straight up, then you'll get 4. Now, be careful about what this 4 actually means. Like, sometimes it would actually have 4 in one of the answer options right here, which is kind of nasty, but they do that pretty often. So just look back in the word problem to see what x actually represents. And that's the number of weeks after July 1st. So you're not done yet. You got to take this 4 and actually plug it back in, because what they're really looking for is the price per pound of beef. So you can take the 4 and then just plug it in for this x right here in the beef equation. That's something I'd like to say more often, is the beef equation, right? I think everyone should. But 235 plus 0.25 times 4. Now, the easy way to look at this is just 25 cents times 4, so that's $1, right? Easy peasy. So 235 plus 1, and then you get 335. And that's a wrap. All right, so number 12. Now, it's saying the line passes through the origin and then has a slope of 1/7. Now, there are 2 basic ways you can do this. One of them I'll recommend over the other for reasons I'll explain, okay? So I'm going to do it the way you would more often want to approach these first, okay? So if they say that you're dealing with a line or something linear in general, you want to default to y equals mx plus b, just because this is the most popular problem type on the test. And getting the full equation of a line is enough to get you through almost anything that they ask you, okay? So if they say that the slope is 1/7, you just plug that in for m right here. So far you've got that it's 1/7 x plus b. Now remember, b is your y-intercept. So that's the point where it crosses through the y-axis. So like basically right there. But they're saying it crosses through the origin. So that would be right here, which makes your y-intercept 0. So let me just remove all that. You know that your b is 0 now. So it's basically this. And then this equation explains the entirety of the line right here. Now, the reason why this is so useful is because you can then go through the options and then just plug them in to see which ones are actually true. Because remember, if you're wondering if a point is on the line, you just plug it in for x and y and see if you come out with something that's true. So if you plug the point in and you come off with something like, 4 equals 2 or something, the point's not on the line. But if you come through something like 4 equals 4, then the point is on the line. So simple enough. So I'm just going to erase that here. And if we go through the options, one of them here is actually bait. So if you plug a in right here, that would look like, remember, x is 0. So 0 would go right here, and then the 7 would go right here. So it's like 7 equals 1/7 times 0. And then 1/7 times 0 is just 0. So 7 equals 0. The point isn't on the line, right? So I'm just going to rewind a little bit here, and we can cross off a. So a is definitely no. And then when I plug b in, it would be like 7 equals 1/7 times 1. This is the one that gets most people, because it looks like the 7s are going to cancel and it's going to be true, but it doesn't end up being true. Okay, so b is out as well. And then if you look at c, 7 equals 1/7 times 7. This would make 1, so it's like 7 equals 1, not that. And I do recommend plugging in the last option even if you've eliminated everything, just to make sure that you didn't mess anything up, right? So this will be 2 equals 1/7 times 14. And then 1/7 times 14 is just 2, and you can see that the point's on the line, so you can confidently choose D. Now, the other way you can go about this, let me just make some room here, is you can graph it. Now, in general, you want to avoid graphing on this test just because it's not going to get you through every type and difficulty of question that they could ask you, okay? They could have given you points that are like 700, 1400, something crazy huge, right? And the only way you'd be able to get through that is by using an algebraic approach like this. So in general, you want to steer away from graphing, but if the points are low enough and you're not going to run into any scaling issues where like your graph isn't accurate or something like that, then yeah, you can go ahead and just, sort of quickly visualize it, but you have to be careful here too. So remember, it's going through the origin, so we can just sort of make a point right there, and the slope is 1/7. So remember, slope goes like this, where it's like up and then over to the right. So if the slope is 1/7, you go up 1 and over 7. So up 1 over 7. Be really careful about what point this actually is, okay? Because a lot of people say that it's 1/7. It's not, though. Remember, it's x comma y. So this is 7, 1. And if you look through here, if you're not careful, you might choose B. Again, that's sort of the trap answer here. But if you make another point by continuing your slope, you'd go up 1 again and then over 7 to the right. So you'd end up at 14 now. My graph isn't big enough. But make your line. And then this is 14, 2. Which is this point. So that's the other way to do this, but again, I definitely recommend the algebraic approach just because it'll get you through even the hardest types of problems involving lines and slope-intercept form on this test. So hopefully that makes sense. Okay guys, so this is number 13. This is the first of our hard problems that we're seeing on the multiple choice for the No Calc Math at Test 1. And yeah, this one deals with an important concept. So it's called, in case you're looking for a name for it, this is simplifying rational expressions. And they call it rational just because it involves fractions or ratios, right? And basically what you're dealing with is you've got two what are called binomials in the denominator here. And if you look, you're adding them. Now, if you think about the basic idea of adding fractions, you do need common denominators before you can put fractions together. So you will need to have these meet up at each one times the other. So I'm just going to sort of copy this down so I have a little bit more space to work with. But a guaranteed place for these two binomials to meet up at is, again, each one times the other. So you just need to multiply this one over here by x plus 3 on the top and the bottom. And then over here, you just need to do x plus 2, top and bottom. And I'm just going to sort of show my work here so things are as simple as possible. A lot of times you do want to leave the denominator here unfoiled. Like you might be tempted to foil these out right now. You don't have to right now. And in some more complicated cases, you'd actually want to leave them in their factored form, it's called, which is when you don't FOIL them out and you leave them like this because something may cancel later on. But in this case, you will end up foiling them. I'm just going to save that for later. So for now, I'm just going to say this is now x plus 3 over x plus 3, x plus 2, plus x plus 2 over x plus 3, x plus 2. And now that these denominators are the same, I can put those fractions together and then add the numerators. So if you wanted to show all your work, it would look like this. Okay, and again, the reason why this fraction ends up like this is if you think about basic fractions like 1/7 plus 2/7, notice how the denominators stay the same when you get 3/7. You don't add the 7s, right? So that's why the denominator just stays the same and we add the numerators. So over here, 1 over, just combine some like terms right there. So you end up with 2x plus 5 all over x plus 3, x plus 2. Now, what you're going to want to notice here is you're taking 1 and dividing it by this big fraction. So this thing in its entirety is called a complex fraction, in case you want to look up some practice with that. It's not that hard, though. A lot of times it helps to write these out horizontally. So really sort of the big picture situation we're dealing with here is 1 divided by 2x plus 5 over x plus 3, x plus 2. And if you think about how you divide with fractions, again, I'll just use sort of a simpler example, but like, let's say you had 3/4 divided by 2/5. What you do with that is, some public schools teach it as keep, change, flip, where you keep this first fraction here, and then you change the division to multiplication, and then multiply by the reciprocal of the second fraction, so flipping the last fraction here. So keeping this, changing this, and then flipping this. So like this. And then you just multiply straight across with these, so you end up with 15 over 8. So very easy, just multiply by the reciprocal of the second fraction. So we're going to keep the 1 the way it is, and then change the division here to multiplication, and then flip the second fraction. So it's like x plus 3, x plus 2, all over 2x plus 5. So now what I'm going to do, since it's 1 times this, it's not going to change the value of this whole fraction here. So all I have left to do is just FOIL this top part, because as you can see, my answer as it is right now is not in here anywhere. So time to FOIL out the top there. So just sort of showing my little swoops here, x squared, and then plus 2x, and then plus 3x, and then plus 6. And then all over 2x plus 5, and then the 2x plus 3x in the middle there, that is going to make 5x. So I'm just going to combine those, and that's what you get. Not so bad. But yeah, anytime you see two rational expressions being added, so like binomials in the denominator like this, you're just going to have them meet up at each denominator times the other, just like I did right here. And that's what you'll do every time with these. So 14. This is where it gets a little bit fun, because you know you're going to be dealing with exponent rules, right? Because you're seeing this guy right here. But if you're going to apply exponent rules, these bases need to be the same. And right now they're not. So we need to address that. Now let me just sort of refresh you on the exponent rules that we're going to be using here. Remember, if you're dividing exponents, then and the bases are the same, then you just subtract the exponents. So you, in this case, you get x to the 4th. And it's important to notice, like, every time when you divide here, the bases will stay the same, and you're just subtracting the exponents to get this here. Okay, so that's what we're going to end up doing here. But as I said, the 8 and the 2 don't match right now, so we can't even apply those exponent rules. But this is a case where they test you on this pretty often, where they want you to re-express one of the numbers as a power of the other. Okay, so 8 could be written as 2 to some exponent. So you're like, okay, well, 2 squared is 4, 2 to the 3rd is 8. So you can rewrite the 8 as 2 to the 3rd and just keep the x out there outside of the parentheses, and then just copy this down. And if you remember your exponent rules, I'll just use another example over here. Let's say you have like x squared to the third. This is called power to a power. And I don't know if you can see that. I'm actually going to write it down here. So x squared to the third. In this case, you multiply these. So this is x to the sixth. Okay, so that's actually what we have going on here. You'll multiply the 3 and the x. So it's like 2 to the 3x over 2 to the y. And now that these 2's match as bases, you can actually divide these and subtract the exponents, and you end up with 2 to the 3x minus y. And then you look back at the problem and you're like, I guess that's why they gave us this. So take the 12 and you plug it in for the 3x minus y, and you end up just getting 2 to the 12. So A, not so bad, right? Now, a lot of people will solve this kind of a different way, where they're like, they see this and right away they want to like get y by itself, which is actually okay, right? So it's like 3x minus y equals 12. So I want to move the 3x over. Oops, 3x, there we go. So negative y equals negative 3x plus 12, and you divide by the negative 1, and then make sure you divide both of these terms by the negative 1. So you get 3x minus 12. So that's actually fine. And you're like, where can I use this? And you might actually get over to this point here. So you're like, okay, well, I'll end up subtracting my exponents. It's like 2 to the 3x minus y. And then you end up taking this and plugging it in for that y right there. So again, this is overcomplicating it, but I just want to show that you can still get there if you like went about this a little bit differently, right? So subtract 3x minus 12. Make sure to put parentheses here because you'll need to distribute this negative 1. And then you end up with 2 to the 3x minus 3x plus 12. 3x's cancel, and you still get 2 to the 12th, okay? A couple other little ways you could go through this, but I definitely recommend the first way that I showed this because this is the quickest and easiest. So, good stuff. 15 is a fun one. So this is a problem involving constants, which I personally love. I think they're really fun, but I'm a math tutor and I chose to do homework for a living. So, take it with a grain of salt, right? So writing this out here, they give you this, and then they say that a plus b has to equal 8. So here's what you want to realize. The factored form of this over here, if you FOIL this out, you would end up getting a trinomial that has this structure, right? So FOIL out the left side and you get something that looks like the right side. So if you think about how you get terms like this, it would be from FOILing. And the way you'd get the 15x squared is by FOILing the first two terms, the ax and the bx. So now you can think like, okay, if a times b has to equal 15 and a plus b equals 8, what could a and b be? So it would have to be 5 and 3, right? So that they multiply to get 15 and then they add to get 8. So what's kind of weird is a could be 5 and b could be 3, or a could be 3 and b could be 5. And that's where these two different c values are going to come from. So what you're going to do is actually plug in each scenario and FOIL them out. And you can actually kind of stop early, which I'm going to show you guys, but for the sake of completion, I'll do both of them out. So again, a is 5, b is 3, start FOILing. And then you get 15x squared plus 35x, and then plus 6x, and then plus 14. So combine those middle terms and you get 15x squared plus 41x plus 14. And this is our first c value, right? Because it's on what's called the linear term, so it's like the x value, right? So c could be 41, that's one possibility. And then I'm just going to FOIL out the second set right now. So it's like 3x plus 2 and then 5x plus 7. And then again, FOILing this out. So we end up getting the 15x squared, and then this is now plus 21x, and then plus 10x, and then plus 14. So combine those middle terms for your second c value, and you get 15x squared plus 31x plus 14. So this is where the 41 and the 31 come from in D. You could have stopped back here if you were super confident, like, oh, I just need to get one c value. And as soon as you see the 41, none of the other options have the 41, so you can stop there. But yeah, with these problems involving constants, guys, just make sure that you are
manipulating one side of the equation to end up matching the format of the other side so you can set corresponding terms equal. So another quick example is like, let's say you had, 2ax plus 3 equals, we'll do 10x plus 6, right? As you can see, the structure of the left side doesn't match the structure of the right. And what can you do? Just distribute. So 2ax would be 2ax plus 6 equals 10x plus 6. And then if you look at the corresponding terms, well, the x terms on the left and right sides have to correspond. Those have to be equal. So it's like 2ax equals 10x. And you can basically divide both sides by 2x. You're not really supposed to divide by x, but we're going to ignore that for now. And you get 5. So that kind of thing. So just manipulating one side of the equation so that it matches the shape and structure of the other side so that you can then set corresponding terms equal and solve for missing constants. That's the name of the game. Okay guys, this is just a quick, easy one just for the sake of completion, right? Remember that once the grid-ins start, the difficulty resets to easy, so make sure you don't overthink number 16 on the no calc section, okay? It's supposed to be easy, so if you find yourself doing rocket science, like back up for a second, okay? So a couple ways you could do this. Most people will just be like, what number squared minus 4 makes 0? And that is just 2, okay? So that is totally fine. Now, the other ways you could do this are like, if you're sort of mathematically neurotic and you want to like show all your work, you could be square rooting both sides and getting plus or minus 2, but then realizing that t has to be greater than 0. So that just leaves positive 2, right? Now, other thing to keep in mind is on the grid in section, you cannot grid in negative answers. If you ever end up with a negative answer on the grid in section, then just go back. It doesn't mean just make your answer positive, okay? But like, look for a mistake that you might have made or a technicality you might have missed. You can't grid in negative answers, okay? So last way to think about this, and this isn't really for this problem because you shouldn't overcomplicate it this much, but you do want to be ready to recognize difference of squares, so like t minus 2, t plus 2, and now that it's factored, it's t equals 2 or t equals negative 2, but again, you'd cross this off because it has to be positive, but just a little extra practice for you guys. Good stuff. 17 involves, if you remember from geometry, similar triangles. So this is a lot easier than it looks, but there are a few things to talk about with this. First of all, just a quick review on similar triangles so you're really, up to date and ready to sort of utilize this, but I'm just going to draw sort of 2 triangles of my own, and I'm doing the best I can to make these look similar. Similar triangles are triangles that have all the same angles, right? But one of the triangles is just a certain number of times bigger than the other. So they have the exact same shape, but one of them is just a little bit bigger, multiplicatively, than the other, okay? So let's say this is 2 and this is 6. You can already tell that the bigger triangle is 3 times bigger, okay? That's gonna help for what we're gonna have next here. So let's say this side is 5, and I ask you to find x. Well, you just say like, oh, well, the bigger triangle is just 3 times bigger, so that would make this 15, and you'd be correct, okay? But for tougher examples like we're seeing here with some bigger numbers, especially on a no calc section, you're going to want to be ready to set up proportions, okay? So there are multiple ways that these proportions could work out. Like you could set up different types that are all valid, but the most reliable one that I find you can use is a sort of small triangle to big triangle, setting up ratios between corresponding sides. That setup, okay? So remember, if you're going to do it this way, with small triangle over big triangle on the left side, you have to do small triangle over big triangle on the right side for the other set of sides. So on the left, you're always going to want to start with a set of sides that you have values for. I just find it to be the most intuitive approach. Again, there are multiple ways you can set this up, but like we have numbers for 2 and 6. That's small triangle to big triangle for the left here. And then we would set that equal to the other set of corresponding sides, small, 5 to x, big. Now, at this point, you really, really want to make sure that you reduce if you can, okay? So 2, 6 just reduces to 1/3, and then the 5 over x is just going to stay the same, right? Remember, whenever you have 2 fractions that are set equal, you will always, always, always cross multiply and set the results equal. That's huge on this test, okay? They give you lots and lots of problems where 2 fractions set equal. Just remember cross multiply. So
in this case, x equals 15, 1x equals 15. So that's what we expected to get, and that's our little review of similar triangles, okay? So that's basically all you need for this. Now, something to keep in mind though, I'm gonna sort of draw an exaggerated example because this is what we're dealing with here. It's kind of hard to see though. So this is what I call an hourglass formation, where let's say you have a situation like this and you're like, okay, 2, 6, and then like 3 and x. So a lot of people think that you would set up the ratio of 2 to 6 for small triangle to big triangle because they're on the same side of the figure technically, but those actually aren't the corresponding sides. So when you have an hourglass formation, the triangles are twisted. So like if you kind of focus on the smallest side of each, the smallest side of the small triangle is the 3, and the smallest side of the bigger one is 6. So those are actually the sides that match up. So you would set up the ratio of like 3 to 6 equals 2 to x. So you have to make sure to go sort of across the triangle like that. And that's what you're going to end up seeing in this triangle over here as well. So I'm going to go ahead and erase this so we have some space. But yeah, getting over here now, a lot of people get messed up with this language where they're saying like respectively. Okay, respectively just means in the same order that was just previously said. So when they say like AB, EB, BD, and then they give you all the lengths, they're giving you the lengths in the same order that they gave you the segments. So that would mean that AB is 1800, right? So I'm going to go ahead and start labeling. So like AB is 1800, and then EB is 1400. So EB 1400, and then BD 700, and then lastly CD is 800. Okay, and they want to know what X is. So you have to be kind of selective about how you set this up. Again, we want in our little ratio here, I personally prefer to have numbers that we have for two sides on the left, okay? So I'm gonna set it up again as like small to big and make sure we do small to big on the right side as well. So if you look here, we actually don't have a corresponding side with this 1800 because the corresponding side would be over there. So we're actually not even gonna use that. But if you look at the 700 and the 1400, in this hourglass formation, those are the corresponding sides because the triangles are twisted once again, right? So you put 700 over 1400. And then, again, we're going small to big, so it's got to be now 800 to x because those are the corresponding sides. And we'll be able to solve for what we're looking for. Again, though, remember the step back here where we reduced before we cross multiplied? Definitely really important for when you're on a no-calc math section, right? So I'm going to zoom out a little bit. I think that'll be the best way to do this. You'll want to use this technique where if you're dividing and you have zeros that line up like this, just go ahead and slash the zeros. It's the same thing as dividing by 10. And if you slash a pair of them like this, you're dividing by 100, which makes sense, right? So now you have like 7/14 equals 800 over x. But 7/14 just reduces to 1/2, so you can reduce that now. Or you could have done it straight away if you're, mathematically savvy, right? But yeah, that's just an easy way to do it. Again, two fractions are set equal, cross multiply, and set the results equal, so it's like x equals 1600. And that's it. Number 18 is another problem that's set up ideally for elimination, okay? So I'm just gonna write a quick note about how you can recognize that. So if both equations have the setup of ax plus by equals c, it's going to be easiest or most efficient to eliminate. Now, here you really could use substitution or elimination just because, you've got a couple variables here that are really easy to isolate, and so substitution would not take long either, okay? But in terms of the optimal, most time-saving approach, okay, elimination is really what you want to go to. You want to be comfortable with both methods because different problems will call for different methods, but in any case, if you're looking for the value of x, think about whether you'd want to eliminate x or y, okay? Because if you eliminate the x's first, then you end up with y as your answer, which you can then go and plug back in, right, to get the x. But what we want is the value of x first. So the quickest way we can do this is to eliminate the y's. So I'm just going to sort of rewrite this here. And if you look, the y's would meet up at 2. So this one's already at positive 2y, so we're just going to multiply this top one by negative 2. And make sure you distribute that to all the terms here. I'm just going to write the results here. And then the other one underneath. And now you just add them. So negative 2x plus x makes negative x, and then the y's cancel, and you end up with negative 7. Then you can just divide both sides by negative 1, and there's your answer, x equals 7. Now, for those of you who prefer substitution, that's totally fine. I'm just going to kind of put that over here. So again, if you're looking for x, the easiest thing to do is eliminate or solve for y if you're going to use substitution. So if you're going to go for substitution here, and here are two equations again. This y up here would definitely be the easiest one to solve for. So I'm just going to sort of rewrite that here. And then you just subtract the x, and you get y equals negative 9 minus x. Since this is what y equals, you can take that and pop it in right there in the y in the other equation. So it's like x plus 2, negative 9 minus x equals negative 25. You distribute your 2. So x minus 18 minus 2x equals negative 25. Watch out for your negatives here. Combine your x's. Negative x minus 18 is negative 25. And then add the 18 over. Negative x is negative 7. Divide by negative 1. And you get x equals 7. 19 is a problem that requires you to have taken pre-calc, but not really also, because you can actually draw this out as long as you're familiar with SOHCAHTOA. This won't give you too much trouble, but it is conceptually difficult. Even some of the highest caliber math kids I've had have had trouble with this problem, and it's very understandable. So as you'll see though, there's a way to get through it. Now, notice how they say that the sine of x degrees is 4/5. You don't know what that angle is, but you can draw your own right triangle. So that's what I'm going to do here. And then I'm just going to put x degrees in one of the leg angles, it's called, okay? And if you think about sine in the SOHCAHTOA acronym, that would be this. And what that means is that the sine of any angle is just the opposite divided by the hypotenuse side. So if they're telling you ahead of time that the sine of 4/5, or the sine of x is 4/5, then you know that the opposite side is 4, and then the hypotenuse is 5, okay? So to deal with this now, the cosine of 90 minus x, I'm going to draw the same triangle again, but I'm just going to pretend that we actually know what the x degrees is to sort of help illustrate something, you'll see. But let's say we know that we're trying to find the sine of 20 degrees. Think about what this angle would be if that's 20. Well, it would be 70, right? Because all three angles have to add up to 180, right? So like 20 plus 90 is 110, and then that would make this 70, okay? Nice little shortcut you can use though. In a right triangle, 90 degrees of the 180 are in this right angle right here. So basically these two will always have to add up to 90. It's kind of important to know for this problem. So think about this. If this one is 20 and this one is 70, couldn't you rewrite the 70 as 90 minus 20? Like, that's fair, right? It still makes 70. So going back to this, if this is x, then this would be 90 minus x. And that's actually what they want. They want the cosine of that angle. So the cosine of 90 minus x, and we think about cosine here, cosine is adjacent divided by hypotenuse. So think about what the adjacent side is for the 90 minus x angle. The adjacent side is this, the 4 in that case. So it would equal the 4 divided by the hypotenuse, which is 5. So if you know the identity where, like, if two angles add up to 90, then the sine of one equals the cosine of the other, you could skip all of this, okay? But if you don't know that, then you can build the triangles the way I did here. I'm going to write out the theorem that I just said really quickly, obviously. But yeah, just because these two angles end up dealing with the same sides, you're going to end up with the same trig value. So 4/5 for the sine of one angle and 4/5 for the cosine of the other. So I'm just going to write that out here. I'll use some purple. So if two angles add up to 90, I'll just call them A and B. So if A plus B equals 90 degrees, then the sine of one of them will equal the cosine of the other. Super, super important, okay? But other problems in this book will also test you on what's called the converse of that, which is the flip of it. So if they start you off with knowing that the sine of one angle equals the cosine of the other, what does that tell you about the angles? It means that the two of them have to add up to 90 degrees. This concept doesn't come up very often on the SAT. In the College Board book, there are probably 4 examples across 8 tests, so call it like every other test that they might test you on this. So not super common, but they could sort of bring it back into the fold down the road. They've been known to do that. So, yep. Number 20. So the last of the grid-ins and the last of the no-calc math questions here. So if you look at what they're giving you, they tell you that a is 5 root 2, and then that 2a equals root 2x, and then they want to know the value of x. A lot of people make a mistake in one crucial step of this problem. A lot of people can get started, but there's one teeny tiny little step I'll point out in a second that tends to get most people, and it's no wonder. But there are a couple ways to go about this. Technically, what you really want to be sensitive to in terms of what will help you throughout all SATs, okay, is when a variable is isolated like this. Because if a variable is isolated or like already solved for, it's your cue to plug it in or substitute it somewhere else. So since a is 5 root 2, you just want to take that and pop it in right there. So you'd end up with 2 times 5 root 2 equals root 2x. And then with rules of radicals, the outside numbers will multiply. So 10 root 2 equals root 2x. Now this is where most people get screwed up. Remember that to cancel a square root, you have to use the opposite operation, which is squaring both sides, okay? So when you do that, this is where most people make a mistake. You have to wrap the entire side in parentheses. So wrap both sides in parentheses, square both sides. This square will hit that square root and they'll cancel each other. This square, this is the tricky part, hits both the 10 and the root 2. So it hits this and the 10. So you end up with 10 squared times, and then the square root and the square will cancel each other here. So it's like 10 squared times 2 equals 2x. And then this just ends up being 100 times 2 equals 2x, or 2x equals 200, and then divide it out, and then x is 100. There's one other way you can do this if you went in a different direction. You just kind of want to know if it works. Some people recognize, well, you know, a equals 5 root 2, and then they say 2a equals root 2x. They're like, oh, well, I just want to do something to this equation that'll make it look like that. In other words, I just want to multiply both sides by 2, which is totally fine because you're doing the same thing to both sides, right? So you end up getting 2a equals 10 root 2, and then I'm just copying this one down here. But since both equations equal, or both expressions equal 2a, then you can set these equal. And you'll just be in the same place that we were before, where you have to square both sides, right? And then you'll just end up getting 100 for your answer. But either way. Again, overall, if a variable's isolated, you'll want to be looking to plug what it equals into another equation, okay? That's what's going to help you with most problems on this test. So, good stuff. Number 1 on the calculator section. So I'm going to assume you guys have already read this, right? But the graph shows his target heart rate at different times during his workout. When is it strictly increasing and then strictly decreasing? The whole strictly thing just means that it can't plateau at all. So these are little moments when it plateaus like that, okay? Because those are just staying at the same rate. So if you look at when it's strictly increasing then decreasing, that should look like a spike, just like this. Right? So going up and then going down, so between 40 and 60. Number 2 is really just some substitution. So they're saying y equals kx, and then when y is 24, x is 6. So you can take the 24, pop it in there for the y, and the 6, put it in there for the x. That way you can solve for what k is, and you'll have the complete equation with k filled in. So it's like 24 equals k times 6, and then you can just divide the 6 out, and you'll get that k is 4, and then you'll just want to rewrite the equation with the k plugged in. So it's like y equals 4x, and then what's y when x is 5? So just take the 5, pop it in there, y equals 4 times 5, so 20. There we go. So number 3 deals with parallel lines, and remember we're still in the easies here, so don't overthink it too much. So they're telling you L and M are parallel. That's like one of the first things they say. And then they tell you that measure of angle 1 is 35, so you can just sort of write that in. Pro tip with parallel lines, basically if the angles look the same, then they are the same, okay? Loosely saying, but like especially for the easies, you can pretty much assume that. So if you look down here at this angle, this would also be 35. And then since these other lines are parallel, like that and that, you can also say this is 35. And then this is what's called a linear pair. So 2 and 35. If you look, they make a semicircle, right? So these guys have to equal 180. So you can just say 180 minus 35, and you end up with 145. So number 4 is, it's still in the easy, so make sure not to overthink it. It's really just coding this sentence into an algebra equation. So like 16 plus 4x in math means equals, and then 10 more than 14 is 10 plus 14 or 14 plus 10, either way, but now you're just solving it out. So 16 plus 4x equals 24, and just move your 16 over, and then 4x is 8, and then you can divide both sides by 4, and you get x is 2. Watch out here because they didn't actually ask for x, and notice how they put 2 in as one of the answer options, kind of one of the nastier things they do. But in any case, they asked for the value of 8x, okay? So make sure you plug it in there. 8 times 2 makes 16, okay? So your answer is actually C. Number 5 is the last of the easies, and if you look at what it's asking for, it's just what's a strong negative association. This just means if you draw a line of best fit or a line through the data, through the middle of it as best you can, it would kind of look like this. Here are all the lines I would draw, lines of best fit. A strong negative correlation just means that the data points are all clustered really closely together, and there has to be a negative slope between, like, of the line of best fit, right? So if you look at this is a negative association because the line of best fit has a negative slope, but it's not strong because the data points are kind of spread out, so definitely not A. This is sort of an exponential line of best fit from what I can tell, so no, and it's definitely not negative, right? Positive slope. This is a strong association, by the way, because the points are clustered really closely together, but it's a positive relationship, so we end up with D because that's negative. Number 6 is testing on something called dimensional analysis or just unit conversion. So I'm going to talk about that in depth in another video, but for our purposes here, it's saying how many 1 milligram doses are there in one 2 decagram container. So what you want to do is start by writing whatever they give you initially. In that case, it's the 2 decagram container. So what you're going to be doing is multiplying by fractions that successively cancel units until you get into the units that you want, which are milligrams, right? So if you look at the initial conversion between decagrams and grams, there's 1 decagram and 10 grams. So you're going to want to arrange the units diagonally so that they cancel. So the question you should be asking yourself is, should it be 1 decagram over 10 grams, or should it be 10 grams in 1 decagram? And you want this configuration because these units are going to cancel just like variables do if you're multiplying fractions like this. So if you were to multiply this out right now, you would be in 20 grams. So 2 decagrams is the equivalent of 20 grams, which does make sense according to this, right? So you just need to keep going one more step here to get it into milligrams. So you chain together another fraction. There are 1,000 milligrams in 1 gram. So again, ask yourself, should it be 1,000 milligrams in 1 gram? The answer is no here because we want these to line up diagonally. We need to have grams here, and we don't right now. So I'm just going to rewind here a little bit. So in 1 gram, there are 1,000 milligrams. This is what we want because now the grams are lining up diagonally, which will mean they'll cancel. And then once you're done here, you can just multiply straight across the top and straight across the bottom. If you want, you can put this, 2 over 1. A lot of people like to do that. So you've got 2 times 10, which is 20, and then times 1,000 is 20,000 milligrams because this is the only remaining unit. So there you go. Number 7 isn't too bad. It's just saying like the total number of installations as 27,500, and they didn't scale the y-axis. So basically what you have to do is look at the total of all these installations here and just add the numbers up. Like city A is 9, city B is 5, right? And then 6, and then 4, and then basically 3.5. Now if you take all those and you add them up, you're going to end up with 27.5. Now the question is, if it's 27.5 and we know it's supposed to end up with a total of 27,500, we have 27.5 what? Tens or hundreds or what? And it's just got to be thousands, because if it's 27.5 thousand, then you end up with this. So yeah, got to be in thousands. Number 8 actually gets a lot of people, so I'm going to do a bit more thorough review of this one. It's not going to take that long, but I'm going to sort of do a quick refresher on what absolute value is. So absolute value is just the distance that a number is from 0. Okay, so I just like to use this example. Like if I have a number line here and here's 0, and then I want to know what the absolute value of 4 is, that would just be 4, because it's 1, 2, 3, 4 units from 0, right? So I could express it like this as well. And then how about the absolute value of -4? Well, that would be 4, because 1, 2, 3, 4 units from 0. So this is also 4. And absolute values never turn out negative because they're just a number of units that the number is away from 0, right? So just straight up +4. Now what you're noticing here is that for negative numbers, it will turn them positive. But for positive numbers, it won't really do anything to them. It just stays positive, right? So what you want to kind of think about is, what is the very smallest number that could ever come out of an absolute value? So a lot of people say like 1, right? But you can actually go a little bit smaller. The smallest thing you can get out of an absolute value is 0, because the distance that 0 is away from itself is 0, right? So that's important to think about here. If you look at this little chunk right here, it's saying the absolute value of n minus 1 plus 1 could equal 0, or can it, right? So in order for this to all equal 0, the absolute value would need to spit out a -1, so that when you add 1 to it, it ends up equaling 0. But you know that's not possible, because the smallest number an absolute value can produce is 0. So there is no such value of n that would ever make this happen. For number 9, they're just looking for the equation that expresses air temperature in terms of the speed of the sound wave. So they're obviously utilizing this equation up here, and you don't even really need to read much of this. I mean, for the next problem you do, but in this case you can just sort of tell that they're manipulating this equation to solve for t, because that's the format of all these. They've isolated t. So that's all we're going to do, is just get t by itself. So I'm just going to copy this down. A equals 1052 plus 1.08 t. Now if you're trying to get this t by itself, you'd want to cancel the 1052 first, just subtract it over. So I'm just going to show my work for both sides here. And then I'm going to switch it around, because it's more natural feeling to have the variable on the left that you're trying to solve for. So it would look like this. And then last thing is to just divide by 1.08. And they leave it like this. So you are done. Number 10 is important for a couple reasons, okay? Now, the very first reason is when they say, what will the air temperature be when the speed of the sound wave is closest to 1,000 feet per second? You'll want to go back to the very original formula up here, and then also the description, because with the way they coded these variables, it's not obvious what means what, really. Like, would you use A to represent the speed of a sound wave? Like, it's not super obvious, right? So just be thorough and double check what each variable means. So notice how they say A is the speed of the sound wave, and then T is more obvious, that's temperature, right? But they're saying the speed is 1,000. So what you want to do is plug the 1,000 in for A. Now you could do it up here in the original, and a lot of people do, but as you can see, I left number 9 up here with the answer, because the answer for number 9 is actually the easiest way to figure this out. It just saves you a couple seconds. This doesn't happen often, but I figured I'd point it out sort of just in case you might be interested. But if you use this formula, look how nicely it just goes in if you put 1,000 in for A and then solve for T. End up with that. Okay. And then you just grind it out real quick. So it's going to be negative 52 over 1.08. And then you end up with negative 48.15. So obviously this guy. Now I'm just going to show you real quick that it also works to plug it in here. So copying this down, 1052 plus 1.08 t. So you can plug the 1000 in for that A right there. And it's just going to look a little different, but you're going to get the exact same thing. I just want you to see that if you use your answer from number 9, this will save you just a couple seconds, right? Because you're having to take just like 1 or 2 more steps, right? So, oops, there we go, 52 and negative. And then divide out by your 1.08, and it's the same thing, negative 48.15. But yeah, pay super close attention, or at least double check what each variable means before plugging it into a 2-variable equation, okay? Just to make sure you're putting it in the right place. A lot of people will put this 1,000 in for t or get confused about where to plug it in. So yeah, just double check in the description. Number 12 is asking for the average number of seeds per apple, okay? So if you just sort of put together a rough sort of word diagram of what that looks like, it would be the total number of seeds divided by the total number of apples, which would give you the average seeds per apple. So question is like, how do we get the total number of seeds? A lot of people just sort of end up adding up these numbers, but this is called a frequency distribution or a histogram. And you have to treat these a little bit differently. With any graph on this test, you want to pay really close attention to the labels on the axes. I know it sounds kind of obvious, but a lot of us ignore it, right? So if you look at the x-axis here and just interpret this first little bar, it says there are 3 seeds in 2 of the apples. So if you're trying to total up all the seeds, it would look like this. It'd be like 3 plus 3, because 2 apples have 3 seeds, right? And then if you look at the next bar, that's like, okay, we got 5 seeds in 4 apples. So we've got 5 plus 5 plus 5 plus 5. Now you're probably seeing this shortcut right now, which is you could just do this as like 3 times 2, right? And then like 5 times 4, which is exactly what you want to do. So this will be 6 plus 20 plus 6, 14, and 27. So I'm just going to write those out. 6 plus 20 plus 6 plus 14 plus 27. And then all over. And then how many apples are there? So what you can do to do this, or figure this out, sorry, is just add up the apples. So there are 2 apples that have 3 seeds, right? So 2, we've got 2 and 4 that have 5 seeds, and then 1 that has 6 seeds, and then 2 that have 7 seeds, and then 3 that have 9 seeds, right? So for all this, you end up getting, well, let's grind that out. So 32, 46, and 27 is 73, all over 12. And then if you do 73 over 12, you end up with 6.08 seeds per apple. And then you're just picking the closest one, so you end up getting 6. And one more thing, I meant to mention this, but I totally forgot. So in this case, they actually tell you the number of apples up top, okay? They won't do that every time though, which is why I showed this whole step, okay? Because you'll need to know how to do it if they don't actually give you the number of apples, right? Or the number of items that you're averaging. But yeah, make sure to pay attention to those titles and the axes, guys. Number 13 is a pretty good one, actually. So they're asking which of the following categories accounts for 19% of all the survey respondents. So the total number of survey respondents is 310. And they're basically asking like, okay, which of these numbers would give us 19% of 310? There are 2 primary ways you can do this, okay? I'm going to show you guys both, but basically, first way is if you look at females taking geometry, females, geometry, that's 53 out of 310. So you can just build the fraction yourself and then just do 53 divided by 310 on your calculator, and you'll end up getting 0.17, which means 17%. Okay, that's pretty close to 19%, but we should keep going and just sort of see which one is closest. Now I might run out of room here, so I'm gonna just sort of make a little space. And then for females taking algebra 2, so we've got females, algebra 2. This time it's 62 out of 310, so 62 out of 310 is 0.2. And then just to save some time, I actually have these decimals written out already. So for males taking geometry, 59 out of 310. That's actually 0.19, but just for the sake of being thorough, we're going to go and do males taking algebra 1 as well. Just make sure we got the closest one. 44 out of 310, 0.14. So we've got our clear winner right here at males taking geometry. Okay, now a really clever way to do this is you can just take 19% of 310 yourself. So 19% of 310, just remember the easiest way to take percentages of numbers is to multiply by the decimal form of the percent. So if this is 19%, you've got to take the decimal place where it is now and move it back 2 places. So you end up with 0.19, and then again multiply by 310. And if we just do that out real quick, let's see what we get. Because I think it's 58.9, okay? And that's really close to 59. And then you can ask yourself which one of these was actually 59, and it is males taking geometry. So yeah, there you go with C again. Either way though. Number 14 is a really good one for developing your math vocabulary, or at least like brushing up on things that you might be forgetting. So they're asking which will change the most here if we take out that last measurement of 24. Okay, so you want to go one by one through these. Mean means average, and then median is the middle number when ordered least to greatest. Okay, range, this is the one that a lot of people forget. So it's the highest number in the set minus the lowest number, which is basically a measurement of the width of the data set, like how much it spans, right? And then this is saying they'll all change by the same amount. So you don't actually have to calculate out the mean. Okay, you could, but to save you time, I'll just say that you don't have to. So the reason you don't have to calculate it out is if you look at how many numbers you're averaging here. Okay, you've got 1, 2, 3, 4, 5, 6, 7. You've got 21. 7 times 3, 21, and of course they tell you here. So 21 numbers that you're averaging. If you take out 1 from 21 numbers, doesn't matter if it's a little bigger than the rest, the average isn't going to change much just because you're averaging so many numbers, right? So probably not the mean. We'll keep it around for now in case we do need to calculate it, but probably not the mean. And then the median, which is the middle number, right? If you just sort of look at the dead middle of this data set, because it is ordered from least to greatest already, it would be this 12 in the middle, okay? Now, if you take out the 24, the median would just sort of move back into this 12, right? Or the average between these two guys. So it's still 12, right? That's not changing at all. So definitely not the median. And then if you do the range, calculate the current range before taking out the 24. So that's like 24 minus 8, which is 16. And then if you take out the 24, now the highest number is 16. So the new range would be 16 minus 8, which is 8. So this is a difference of 8 when you find the difference between the ranges, right? So that's a huge difference. The mean would probably change by some small decimal or maybe like 1, right? But yeah, not nearly as much as the range, and they definitely don't all change by the same amount. So there we go, just the range. 15 is pretty important just because it provides a nice review of something kind of important, right? In slope-intercept form equations, your m, or your slope, is always your rate of increase or decrease, right? And then your y-intercept is always your starting amount or a flat fee. So in this case, we're renting a boat, okay? And even if you take it out for 0 hours,
it's still $5. So this is the whole idea of a flat fee. Like if you're going to rent a car, right, they might charge you $100 like straight up and then $50 for every day that you have the car or something like that. The $100 would be that flat fee that they charge you no matter what. And this is the same idea. They're going to charge you $5 before you even take the boat out, right? So if we just use different variables according to what they're saying here, they say the total cost C is the new sort of y-axis, right? And then taking the boat out for h hours, that's your new x. So it's like C equals m times h plus b. But you can see that your b value, your y-intercept, is the initial cost of renting the boat, the c-intercept. Number 16 is the first troll problem on the SAT thus far in practice test number 1. Okay, and you'll see what I mean in a second. They want the relationship between h and c. If you look at all these, there's 2 variables, right? In every example. This is slope-intercept form in disguise. Like a lot of people will recognize this. But when you go to get the equation yourself, just sort of visually, you know that the y-intercept's going to be 5, right? So not a big deal. You know it's like y equals something x plus 5. And then we'll change the variables later, right? And then most people go, okay, well, I'm going up 3 and then over to the right 4. So it should be y equals 3/4 x plus 5. And then when you change the variables over, it'd be c equals 3/4 h plus 5. And then they choose b. But this is wrong, okay? So I'll show you why. Look at the way they scaled the x-axis. This is not very nice, but it's something you have to sort of expect from them. So instead of going up 3 and over 4 units, you really only went 1, okay? So that means that, let me just erase this so no false advertising. So you really went up 3 over 1, and then your initial amount is still 5, right? But when you change it over, it ends up being this. So there you go. Again, watch out for those axes labels and also how they scale them, because you can run into stuff like this. They did put B as an option, which was there to lure you, right? But yeah, gotta be C. 17 is a good exercise as well, because they're asking for what value of x is the value of f of x at its minimum. What a lot of people will do here is they'll say, oh, there's the minimum right there. It's -2, and then they'll choose -2, right? That is the minimum, but that's not what they want. I'm just going to sort of double underline this. What value of x? They want the x value at this minimum, which is -3. And of course, they put -2 as an option. Number 18 is actually crazy important because it includes something that you'll see really, really often, and that is a point that they're giving, okay? So I would actually write this down in your notes because it is that important. I'm going to make a special note of it over here. If ever given a point, always, always, always plug it in for x and y. Most of the time, this will get you through 95% of the problem. That's really all they're testing you on, is knowing to plug this in, right? So just to show you what I mean, like the 0 goes in for x, right? And then this 0 goes in for y. And you're going to be plugging it into both of those inequalities. So it's going to look like this once you plug it in. So I'm just going to do the top one first and just show the raw plug-in before I do anything else, right? Now, I'm going to simplify this. -0 is obviously just 0, right? So you end up getting this and then this. And having the variable on the right side with an inequality is really backwards feeling. You don't want to keep this as 0 is less than a, because that's really confusing to try and visualize, okay? You want to flip it around so that you have the variable on the right side, but see how it's like a is greater than 0 if you read it from the variable's perspective? Make sure you're flipping that sign so that it's true when you flip it like that, okay, or it's the same. So now I'm going to show the plugin for the second inequality here. So it's like 0 is greater than 0 plus b. So 0 is greater than b. And then flipping it around, you end up with b is less than 0. So if a is greater than 0 and b is less than 0, what do you actually know? Well, definitely that a has to be bigger than b, which is that. So you can see that plugging the point in got you through most of this, and trying to do this abstractly with a system of inequalities like we're seeing here is much more difficult than just plugging in the point. So plug in that point.
19 is super important because it includes a structure that is super, super common throughout this test, okay? And this is systems of equations, word problems. So for these, it's not going to be every time that they take this shape, but it's just such a common structure that I am going to point it out. The most intuitive equation to code first is the total money made. And then the less intuitive one, although it's simpler, is the total quantity sold. And you'll see how this applies here. But yeah, those are the two equations we're looking for. Now, if you look here, they're selling the salads for $6.50 and then drinks for $2. And then it says they sell a total of 209 salads and drinks, and they make $836.50. So if we just sort of code these one at a time, the total money made, you have to think about the amount of money that you would make from salads alone, right? So since salads are $6.50 each, it's going to be 6.5 times the number of salads that you sell, right? Selling salads has always been a dream of mine. I don't know if you knew. So 6.5S gives the total money from salads. And notice how I'm using S instead of like X and Y, okay, for drinks. This is really important just because when you solve for a variable, a lot of times if you're using X and Y, you won't double check what you coded as X and Y. It's way better to use first letters of the words that you're representing, like S for salads and D for drinks, just because you're not going to mess up like which ones you're solving for versus which ones they're asking for and all that kind of stuff. So yeah, whenever possible, use first letter coding like that. So 6.5S is the total amount of money we pull in from salads, and then from drinks is $2 each. So plus 2D would make the total amount of money they made, which is $836.50. This is sort of, like I was saying, the harder one, the total quantity sold. We sold a total of 209. Well, S is representing number of salads that we sell, and D is the number of drinks. So like, what do you do with the variables S and D to express that you sold a total of 209? You really just add them. Salad number plus drink number is 209. That's the one that gets a lot of people, right? So question is, what are you going to do from here? A lot of people feel more comfortable with substitution, which you certainly can do. These are not hard to solve for, right? But remember, if both equations are set up like this, ax plus by equals c, it is most conveniently set up for elimination, okay? So don't be afraid of using both methods. In some situations, you really need to use elimination because these variables aren't easy to solve for. Like I said, in this one, easy to isolate S or D if you really want to use substitution, but it is better set up for elimination, so that's how we're going to do it. And then if you look, like, which one is the easier variable to eliminate, you could do either one, but definitely D, right? So multiply the bottom by -2, and then I'm just going to copy the top one like this. And then after distributing the -2, we're going to end up with -2s minus 2d equals -418. And then when you add downward, 4.5s, and then the d's are gone, and then you end up with 418.50. It's also a good thing that we eliminated d because what they're looking for is the number of salads. So if we want to get to our salad number first, when you say like, oh, this is how we first get to our salad number, right? Yeah, check that off the bucket list. So divide both sides by 4.5. We wanted to eliminate D because it leads us directly to our salad number. This problem's ridiculous. I don't know. There you go, B. All right, guys, so 20 is actually kind of a beast. It's the hardest percent problem in the entire book, okay? So I'm going to try and go through some percent concepts relatively quickly because I'll do a separate video on percentages and all that kind of stuff. But you will need to know a couple of key little shortcuts for this problem. So first thing, okay, this is what I would call instantly increasing or decreasing by a percent. Okay, so I would call these tax and discount multipliers. So I'm going to use my own example first, and then we'll sort of get over to number 20 here, but let's say you had like a $200 bike you wanted to buy, and there was 5% tax. That's nice to imagine, right? So a lot of people would be like, if I asked for the final price, they would say 200 times 0.05 would give me $10 in tax, which I would then add to the $200 bike. So $200 bike plus the $10 tax gives me $210 total, okay? And this is correct, but for problems like 20, you need to be aware of this shortcut that I'm going to show you called a tax multiplier. So instead of multiplying by 0.05 to get the tax number alone, you can actually start at 100% because you're going to pay 100% of the cost of the bike, right? But then because you're paying more with tax, you're going to add 5% to that and end up with 105%. Now, this actually makes sense because if you're going to pay 100% of the cost of something, that's just the cost itself, right? But if you add 5% to that and you're paying 105% of the cost, that's the same amount of cost for the bike, but just a little bit more, right, to include the tax. If you turn this into a decimal, that's 1.05, and you multiply 200 by 1.05, that will lead you directly to the final cost without calculating the tax separately first. This is a crucial tactic for problems like this, as you'll see in a second. So there it is with a tax multiplier. Now, I think I'm gonna sort of zoom out here just to make a little bit more room, and then I'll end up erasing and stuff, but whoa there, boy. Okay, so now for a discount multiplier, I just want all this to be on screen at the same time. You'll see why in a second, but let's say this time you have a 5% discount. So again, you could calculate this in two parts, right, and do like the 200 times 0.05 to find the final price. It's still, $10, but this time that $10 is a discount. So you do 200 minus 10 to find the final cost, and you end up with $190 total, which is correct. But again, for problems like 20, you're going to need to know the shortcut, which is go over here at 100%. Because it's a discount this time, you're going to be paying less than 100% of the cost of the bike, right? So you subtract 5%, and you end up with 95%, which as a decimal is 0.95. So if you do 200 times 0.95, once again, it'll lead you directly to the final cost of 190 without you calculating the discount out separately first. This is super important because let's say you are going to be taxed but also get a discount like you are in 20 here. You're going to want to know about these tax and discount multipliers so you can chain them together. Okay, so here's what I mean. We're going to go ahead and erase this. There's my little note for don't draw past here because my little webcam is up there. But okay, so going back in here, if you look at what they're saying here, they gave a 20% discount off its original price. So if you're thinking discount, you're like, okay, that's 100% of the cost, but you subtract 20% because you're getting a discount. So the discount multiplier, when you convert it to a decimal, will be 0.8. I'm going to label that as the discount multiplier. And then you also have to pay 8% sales tax. So you'd start at 100% and then add 8%. Like, okay, this is 108%, which as a decimal is 1.08, and this becomes our tax multiplier. So if you notice the structure of this, it's saying at the cashier she paid P dollars. So they want the original price. Assuming you had the original price, you'd be like, okay, you get a discount, so 0.8, and then times the tax, 1.08, and then times X for whatever that original price is. And then you end up paying P dollars at the cashier. So if you look at what they want, again, it's the original price. So this is what they want you to solve for. And it's kind of funny looking, but if you want to solve for this, you can just divide both sides by these two multipliers both at once. So when you divide, it looks like that. And this is an expression for the original amount or the original price of the product. So you end up with D. Again, hardest percent problem in the book, but as you can see, you really did need to use the discount and tax multipliers in order to save yourself a lot of work. Technically, this is possible to calculate in two pieces, like, okay, just calculate the discount amount in terms of X and just calculate the tax amount in terms of X, but it would just create a lot more trouble for you than it's worth. So yeah, definitely get familiar with these percent or these discount and tax multipliers. They're very, very handy for the hardest percent problems in the book. Okay guys, so 21 gives people a lot of trouble, and with good reason. It's kind of an awkward process. You have to build probabilities not from everybody, but from a specific subgroup that they specify. So we're just going to talk about how to do that real quick. So I'm just going to write this down because this note kind of helps. It's sort of a formula for this. So building probabilities. What you'll end up doing is putting the number of, I just call them winners, or like the desired group, over the subgroup you're picking from. So again, in this case, it's not everybody, it's not all 200 people. If you look down here, I'm just going to underline the group that they're picking from. A person is chosen at random from those who were called at least one dream. So if you look up here, that's these people and these people. And the easiest way to get these numbers, the totals, are in the total row right here. So just add those guys up. So I personally, for some reason, think the denominator or the subgroup is easier to identify first, just because it's the harder thing. So like once you get that out of the way, it just becomes easier from there. So we're picking from 164 people. That's what you get when you add those. And then what's the probability that the person belonged to group Y? So basically on the bottom, we've got at least one dream. And then the top would be group Y, at least one dream. So if you look at that, that would be these guys up here, because this is group Y, and then 1 to 4 or 5 or more. So you add those up. 11 plus 68 gives you 79 over 164, which is C. So again, guys, really utilize this formula. I think it's easier to identify the subgroup that you're picking from first, just because it gets it out of the way. It's sort of the harder thing they're testing you on. Most people can identify the desired group without much trouble, but the subgroup is oftentimes what is much more difficult. So yeah, go with that first. Number 22 is not super common as a problem type anymore, but they'll test sort of loosely on the same thing in a couple different problems in this book. So it's worth going over. It's a good thing to know. So if you just notice here, they're looking for the average rate of change in the annual budget for agriculture and natural resources. So we'll just hone in on that up here. Hang on, let's make a better circle. There we go. Okay, so in Kansas from 2008 to 2010, so that's 2008 to 2010. The average rate of change formula is simply just the total amount of change divided by the total amount of time it takes for that change to occur. That's the average rate of change. So there we go. And then if you think about amount of change, think about what you should be doing with the numbers, okay? If it goes from 358,708 up to 488,106, the amount of change would be subtracting those, right? So 488,106 minus 358,708 divided by, technically it's like 2010 minus 2008. This is just a slope formula, but you could commonsensically be like, that's 2 years, right? So the number you get from this is 129,398 divided by 2. And then once you do that out, 64699. And the closest option is B. So we got something that was in thousands because the table is expressed in thousands. So basically, like, it's this many thousand, which really means this as the number, which is 65 million. Number 23 isn't super popular as a problem type either. In fact, I think they've kind of phased out problems like this just because they're kind of time consuming, as you'll see with how you have to calculate these, because you're basically calculating ratios between some pretty big numbers, and it just takes time to crunch them all out in your calculator and see what you're getting for these decimals, and you kind of have to do them all out to see which one is closest to what they're asking for. So just to point this out here, they want to know which one's 2007 to 2010 is the same as the 2007 to 2010 for human resources. Okay, so if we head over to human resources, 2007 to 2010, so I'm just going to sort of calculate that out here. 2007 is 4051050, and then 2010 5921379. So you're going to calculate this out, and you'll end up with 0.68 when you divide those. Okay, this is the decimal that you're looking for. You're wondering which one of these is going to end up as close as possible to 0.68, right? Now, when you're doing this, very minor time-saving tactic is you could just sort of work with the first 4 digits of all these numbers. That'll get you close enough, but I wouldn't do like the first 2 digits, okay? It's not going to get you accurate enough of an answer. Just because these decimals do kind of float around the 0.7 range, so you're going to need, to go probably this far to stay accurate. But I'll just sort of we'll do out the first one here, and I'll show you how you'd build this. So for agriculture, natural resources, again, you're doing 2007 to 2010, so it'd be like 373,904 over 488,106, and from this you get 0.77. Now, what you want to do is just sort of like put I'm not sure if you can see that over there. I'm just going to make some room right here. So put the decimal associated with each answer next to it like this. So this is how you build each one of these, but for the sake of time, I'm just going to give you the decimals that you would get. Education ends up being 0.72. Highways and transportation is 0.82. And then for public safety, 0.56. So as you can see, agriculture, natural resources, and education were pretty close, so you don't want to round too much or chop off too many digits, when you're calculating these ratios. But the closest one to the 0.68 ends up being education at 0.72. 24 is a good one for several reasons, okay? First reason is it provides a nice review of how you graph circles, okay? So for a lot of people, 24 is the first time they see a problem involving graphing circles. A lot of it, unless you've taken pre-calc, or like a nice challenging algebra 2 class, you may not have seen how to graph circles yet, but they're actually really easy. So I'm just going to sort of lay out the formula here for you. You end up with this, and then in this formula, the center of the circle is at HK, and this number you're going to see at the very end there, that's the squared version of the radius. So R obviously represents the radius, right? So for example, just as something quick, let's say you had like x minus 3 squared plus y plus 2 squared equals 25. So what you have to remember is that there are negatives built into the formula here and here. So when you see an x minus 3, that's really a positive 3 that got plugged in for h, right? And then over here with the positive 2, that's really a negative 2 that got plugged in for k. And the minus negative is what turns it into a plus 2. So bearing that in mind, the center is the opposite of each of these coordinates. So it's like 3, negative 2. And the radius, remember, this is the squared version of the radius that you're seeing. So if you get an r squared of 25, square root it, and you get 5 for the radius. Now in terms of how you actually graph that, because you'll need this for other problems, go and mark your center at 3, negative 2. I mark it with a hollow dot because it's actually not technically part of the graph. The graph is the circle itself. So from here, notice how your radius is 5, right? You'll be going up 5, so that would bring us up here to 3. Down 5, so that's down here to negative 7. Right 5 to 8. And left 5 to negative 2. And then you just connect it with a circle. And that's how you graph circles. Not a big deal. Hopefully you draw them a little better than I do, but yeah, circles are kind of challenging to draw. So yeah, that's graphing circles. In terms of what you'll need for this problem, you'll need to know this formula, which we'll be using in a second. Okay, so I'm going to rewrite that, but make some space here. Okay, so again, we know we're dealing with the equation of a circle, so we're just going to write this down ahead of time. Oops. And then notice how they give you the coordinates of the center, right? That can go right in for h and k. And then you don't know what the radius is, but they also give you an endpoint, right? And I'm going to write this again. We did this out in another problem, but if ever given a point, this is such an important piece of advice, I can't overemphasize it. So if ever given a point, always plug it in for x and y. Okay, it's a huge part of most of these problems. So I'll just simplify this a little bit with the center coordinates plugged in, right? Because it's like x minus 0 squared plus y minus 4 squared equals r squared. The x minus 0 squared will just simplify to x squared, which makes sense, right? And now that this is sort of simplified, we're going to take the endpoint coordinates and plug them in for x and y. So make sure you use parentheses when you plug in fractions. You'll see why that's important in a second. You'll end up with this. And this is how you're going to solve for the radius. When you square a fraction, if you're forgetting how you do it, just write it off to the side, because squaring just means multiplying it by itself, right? You multiply straight across, and you get 16 over 9. Now, the easier way to do this, though, in my opinion, you just have to remember that this is the way it works. You have to square the top and the bottom. So 16 over 9 plus 5 minus 4 is 1, and then squared, so 1 squared is 1. So you end up with this. Now, with circles especially, you're going to want to make sure you stay with fractions. A lot of people are tempted to go to their calculator and get decimal versions and all that kind of stuff. You want to stay with fractions because if you notice the radius expressions, those are all in fractions, okay? So just put the 1 over 1. You're adding fractions, so you need common denominators. So you're like, okay, times 9, and then, so it's 16 over 9 plus 9 over 9, 25 over 9 for r squared. Now, if you wanted to get the radius, you could square root both sides and get 5 over 3. You don't need it for this problem, but for other ones you will. So that's how you'd get your radius. But our main objective was to get the r squared, so we could then plug it back into the formula. So take your r squared and plug it back in here, and then your final answer is x squared plus y minus 4 squared equals 25 over 9, which is A. So 25 is actually a pretty important problem because it involves a really specific form of factoring that a lot of people forget how to do. So we are going to take it pretty seriously here. If you notice the question, it's saying after how many seconds, so we're looking for a time. That's important to, whoa, that question mark was jacked. There we go. Okay. So after how many seconds will the ball hit the ground? A lot of people get confused about this part. They're like, okay, hitting the ground. They can't sort of figure out what to plug in, where. But if you visualize this is a ball being launched from the ground, and it's a quadratic, right? So it's following this parabolic arc, it's called. So think of like punting a ball, right? So this is the height, and this is the time. And if we're talking about hitting the ground, that happens right there. And a lot of times you just want to ask yourself, if you're looking for something, like what do you actually know about that point? And we don't know at the time, okay? So let's be clear about that. We're trying to solve for the time. So think about the height though. When it's hitting the ground, we know the height is 0, which tells you what to do actually. We want to plug in 0 for the height. So in this, plug in 0 for the height. And I'm just going to use a simpler example to help us sort of figure out how to solve here. A lot of people are tempted to square root, but you're not going to be able to because you've got a t variable over here as well. This is what I call ax squared plus bx equals 0 factoring. Because usually you have like a little c term here, and then that would mean just normal factoring, which everyone's used to, right? I won't go through that too in depth here, but with this type of factoring, this is an example. Let's just say it's like x squared minus 6x equals 0. When there's a c term missing, or like c equals 0 in other words, all you have to do to factor this is GCF an x out. So when you pull the x out, it ends up with x minus 6 in parentheses like this. And then since this is factored, you use zero product property, it's called, which is where you're setting each of the factors equal to 0. So this outside factor could be 0, and then this one could be 0 as well. And then you just solve. So in my example, x could be 0 or 6, which actually makes sense. Like if you plug 0 in here, and then you multiply it by whatever that becomes, happens to be -6, but it doesn't even matter. 0 times anything is 0, right? So 0 is one of the solutions. And then if you plug 6 in here, then that would also make everything 0, which would make it a solution. So that's why this works, right? Ours over here is a little bit more complicated, but it's the same idea. Like we have a t squared and a t. We have no c value over here. So you just GCF a t out, and this is what's left. It's like -4.9t plus 25. And then you're ready to set each of these equal to 0. So time could be 0, which actually makes sense because it started off on the ground, right? Like we launched it from the ground. So when the time was 0, the height was 0, okay? But we're more interested in the other solution. So you get that from setting this equal to 0 and just solving. So you end up dividing by -4.9 here. And what you get is 5.1 seconds, but the closest answer to that is D. 26 is a great practice problem for percents, okay? Because we're dealing with a percent more or percent less situation, and it's really, really good for clarifying some percent questions that people have, which I'll sort of explain here. So first thing we want to hone in on is type A trees produce 20% more pairs than type B. So a really simple sentence that we could use to help us code this algebraically is A is 20% more than B. So the 20% more than, if you remember from number 20 in this section, it's easier to instantly add or subtract a percentage by using a percent multiplier, okay? So instead of finding what 20% of B is and then tacking on another 20% to find out what A is, you'll want to just sort of look at it as 100% plus 20% is 120%. This is how you code 20% more. So A is 120% of is the way you can understand that, B. So now the decimal form of 120% is 1.2 because you move it back 2 spaces, right? And then of is always multiplication, and then just B. So I'll just write it down here a little more neatly. This is how you say A is 120% of B, or in other words, A is 20% more than B. That's the easiest way to code this, okay? So now that you have this equation, which simplifies the whole situation, highly recommend getting this first, right? You can take the 144 that they say A is and just pop it in right there. So you have 144 equals 1.2b, divide by the 1.2, and you end up getting b equals 120. So this is the easiest way to get there, and it's going to help you to understand this for future problems that are a little bit more difficult, right? Like if you go back to number 20, that's a great example of it. So a lot of people try to sort of reverse engineer what's happening. They're like, okay, if A is 144 and that's 20% more than B, well, can't I just take 20% off of 144? And the answer is no, because you're working from a different base number. Remember that B is 120, right? So if you do 120 and then you like take 20% of that, that's 24. And then if you add it on, there's the 144 for A that we were expecting, right? But if you take 144 and then take 20% of that, that's going to be what, 28.8? And then if you subtract it, 28.8, let's just crank that out real quick. So 115.2. Notice how that does not give you the correct answer of 120, right? And it's also bait right there. But it's all basically
because you're taking a percent of the wrong base number, okay? So make sure you always code it directly from the way they say it, which is this right here. A is 20% more than B. Code it by finding the percent multiplier this way and get your equation and then plug it in and solve. That's the safest way to go about these. 27 is kind of weird. I haven't really seen a problem like it since. Not too big a deal, but there's like one really tricky part that we'll get around to talking about very shortly here. So they're wondering what a reasonable approximation is of the number of earthworms beneath the ground surface in the entire field. Okay, so if you're just looking at all these numbers, they're sort of hovering around 150, which is why you see all these 1.5s here, right? And as you can see, it's just a question of sort of the order of magnitude, like 150 times what in terms of the total number. So what a lot of people will do is they'll count these regions, okay? And they'll be like, okay, well, those are 10 regions. So they'll do 150 times 10 and get 1,500. And then they'll think it's B, which is totally reasonable. But if you look at the description, it's a square field that measures 10 meters by 10 meters. And then each region is a square that has a side length of 1 meter. So I'm going to sort of very quickly draw this, so excuse the poor depiction. But what's happening is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 makes 10 regions. And then they do it this way too. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so if you were to count these up, right, it's 10 by 10. There are actually 100 regions in this field. And the nasty thing they did was they took a sample of 10. So like all those regions you're seeing are just like 10 random little samples from in here, but that doesn't represent how many earthworms there are in the entire field. There are 100 regions, not 10. So it's 150 times 100, which makes 15,000. So the answer is C. So 28 is testing on graphing linear inequalities. It's technically a system of them because there are 2 of them, right? And there's just one crucial part about inequalities that most people forget that makes this hard. So this is actually the first multiple choice hard in the calculator section. 28, 29, and 30 are the hards. So if you look here, you would actually just graph this as if it was a regular slope-intercept form line, which means you would start up here at 1 and then just go up 2 over 1. It doesn't have to be exact, but it looks basically like this. And then just ask yourself, is it a solid or a dotted line? And because of this little equal to right there, this little bar underneath there, it is going to be a solid line because any point that works could actually be equal to this line, or in other words, on the line. So you make it a solid line. And then just use a simple trick for the shading. If y is greater than, does that mean above or below? Well, above, right? So if it says y is greater than, shade above. So loosely sort of like that, right? I'm going to use a different color for the next piece, this guy. So same kind of thing, just go down to -1 and then go up 1 over 2. And then this time, because there's no little equal to right there, we are going to use a dotted line. So it's like this. And then do we shade above or below? And because of the greater than, we are going to shade above. And then here's what most people forget, right? The solution set to a system of inequalities is actually the overlapping region, okay? So this, I'm going to use some purple. This is where they actually agree. So there is no purple region in quadrant 4. So that's where there's no solution. A lot of people pick D because they're like, oh, there's a little bit of red part in 4. So they all kind of have a solution. But remember, it's the overlapping region that's the solution to a system of inequalities. And quadrant 4 doesn't have any purple. So there you go. Okay, so full disclosure of number 29. This type of problem really isn't on the tests anymore. Practice test 1 is actually a very old test. So I don't think you'll see anything like this, though. You know, they could bring this back around, and it is probably the hardest problem in the book conceptually. It's just the most niche knowledge. As you can see in a second here, it's not terrible, but it's one of those things where you need to know a couple things in order for it to be fine, right? So I'm going to sort of do a cursory explanation of this
just like what you need to know essentially to solve this problem. And then off to the side, I'm going to do a little bit more in-depth of a review, okay? Just I'm going to add a little something. So first thing I'm going to do is come up with my own function for our purposes, right? I use this function a lot when I'm teaching, synthetic division and long division and stuff like that. So I'm just going to use this. We're going to let this be p of x. And what we're going to do is actually do some polynomial long division. I'm just going to divide it by x minus 2, just so you guys can see the way that turns out and the remainder relationship and all that kind of stuff. So if you guys need a review of polynomial long division, I'm probably going to do another video about that. But in the meantime, I'm going to go relatively quickly, so just pause the video if you want to sort of digest the steps a little bit more slowly, okay? But I'll try to put it as simply as I can here without going too slow. So very first step in polynomial long division is you're trying to get this term up to this one using multiplication. So like, what do I multiply this x by to get up to x to the third? And it will be x squared. Now I recommend putting this above the 6x squared because this will be your x squared column, this will be your x column, and this will be your constants column. It's just a nice way to stay organized. And also when you're here, you know that you're done. Okay, so it's not totally mandatory. Most teachers don't teach it that way, but I like to just because it's nice organization-wise. So now that you have the x squared here, what you're going to do is distribute it into this and then subtract the result as a quantity from this. Okay, so x squared times x, I'm just going to erase a little bit. So the x squared times the x here, that is x to the third, and then minus 2x squared. And then remember you're subtracting here, okay? So you have to do the opposite of whatever's in here. So it's like x to the third minus x to the third will cancel these. That was the whole idea. And then 6x squared minus negative 2x squared is 8x squared. And then bring down your 11x. And now the process restarts here. So now you're trying to get this far left x. This term doesn't matter, by the way, in case you're wondering, like you never actually look at that one. It's always the far left term. You're trying to get this x up to this 8x squared using multiplication. So that would be positive 8x. I'm including my sign here, that's important. And remember now we're just distributing the 8x into this and subtracting the results from here, okay? So 8x times x would now be 8x squared, and then 8x times negative 2, so negative 16x, and then subtracting these will go away, and then 11x minus negative 16x, 27x, and then process restarts after bringing the 6 down here. So now it's, what do we multiply the x by to get up to 27x? And that would just be positive 27, which we're then going to distribute into this and then subtract from here. So subtracting 27x and then minus 54. So these guys cancel. 6 minus negative 54 is 60. Okay, this is the important part here. This is actually your remainder. So the remainder is expressed as plus remainder over what's called your divisor, so this guy right here. So you will need to know how to do polynomial long division for a lot of the tougher problems in the book and on the test. So this is a good review, okay? But the next thing I'm going to show you is, notice how we divided by x minus 2, just as sort of a sample exercise, right? Watch what happens if you plug in positive 2, so the opposite of this sign, into x, okay? So it'll be 2 to the third plus 6 times 2 squared plus 11 times 2 plus 6. So 8 plus 2 squared is 4 times 6, 24. 11 times 2 is 22. And then I'm just going to sort of pair these up. 32 plus 28. P of 2 is 60, which is the same as the remainder. Okay, so what you're seeing here is an illustration of something called the remainder theorem, if you want to look that up. I think it's expressed a little bit, in a bit more of a complex way online, so that's why I like to draw it out like this. But basically it means if you just plug the opposite sign of what you're dividing by, like if you're dividing by x minus 2 and then you plug in positive 2 like we did here, you're going to get the same remainder as if you actually did out the long division and got it this way. So when they say that the p of 3 is negative 2, remember it's the opposite sign that you're seeing inside the parentheses right here. So it must mean that they took p of x and divided it by x minus 3 and got a remainder of negative 2. So that is this. Okay, so that's the essential portion of this problem. The extension I was going to do from this here was, let me just erase this. A lot of people think of synthetic division and synthetic substitution, rightly so, when they see stuff like this, because this is how it's presented in Algebra 2. But let me just make this here. So this is how it looks in synthetic division. So with synthetic division, if you're actually going to do it out, you put the coefficients of your dividend, it's called. That's the thing you're dividing. Okay, I'm just going to be dividing this by x minus 2 because that's the sample we're going with for this whole exercise, right? But 1, 6, 11, 6, and then again, take the opposite sign of what you're dividing by. So we're taking this and dividing it by x minus 2, just to see what happens here, right? So opposite sign of this goes here. Now with synthetic division, if you remember, and by the way, there are technically no synthetic division problems on the SAT as of right now, okay, as of 2021. They may bring it in at some point because they sort of tweak and develop the test and, update it test after test. So it is something they could bring in, but for now it's not technically on there. Sometimes you could use it if you wanted to do something a little bit more quickly than you would with polynomial long division, but remember, you can only use synthetic division when you're dividing by what's called a degree 1 divisor. So notice how we're dividing by x minus 2. The reason why we're able to use synthetic is because this is x to the first minus 2. If this was x squared minus 2, you wouldn't be able to use synthetic, right? So doing synthetic now, if you remember, this first number here, in this case the 1, you just bring that down and copy it, and then it's 2 times 1, 2, and then you add them. 8, and then 2 times 8, 16, 27. These numbers should be looking familiar at this point. 2 times 27 is 54, and then 60. So once again, there's your remainder, okay? But if you're looking at this process as synthetic division, what you can actually see here is that you have the coefficients of your result. Like if you remember if you just rewind, our answer for when we did this with polylong, it was 1x squared plus 8x plus 27. Your first exponent here is always one lower than what you started with in your dividend, okay? So since we were dividing x to the third by something, we know our answer will start with x squared and then just descend in x's from there. So this is actually our answer in the synthetic division process here, which is the same as what we got from polylong. Now with synthetic substitution, this is what's so confusing about synthetic substitution. The process is virtually identical, but the way you interpret the results is a little different. So again, I'm just going to sort of power through this. Bring down your 1, multiply by 2, so 2, and then add, and then 16, 27, and then 54. And 60. Only with synthetic substitution, what you're doing here, the way you're interpreting the results, is that this is the result of doing the p of 2, or just plugging 2 in. All it's meant to do is expedite or make quicker the results of substituting 2 into the function, okay? So the way this problem is structured, knowing that this is the remainder when x or p of x is divided by x minus 3 is very much a synthetic substitution idea and synthetic division idea. So there are a couple different layers to this. All you really needed to know was the first part, the relationship between polynomial long division and substituting directly and how they both give you the same remainder. But yeah, that is probably the hardest problem in the book. It requires the most niche knowledge in my opinion. But I haven't seen anything like it since, so don't sweat it too much. It's just if they do bring it back, you would want to be ready for it. Number 30 is a good one, actually. So it's the last of the multiple choice hards on the calculator section. And we want to look at the question really carefully here because they're asking for something super specific. It's not actually that hard, but there's sort of a trick. There's a little bit of a bait answer here, which we'll talk about. But if you go down in here, so they want an equivalent form of this equation where the coordinates of vertex A have to be identified as constants in the equation. A lot of people just sort of glaze over this and think it's just like math jargon, right? But they're actually asking for something really specific. What most people will do is they'll take this and they'll be like, oh, I know how to factor. Okay, so what multiplies to get 15? Well, we've got 1 and 15, and then we've got like 3 and 5, and then which of those pairs could add to get -2? Well, it'd definitely be the 3 and the 5, right? So most people are like, okay, -5 and +3. And then they're like, sweet, okay, that's it. So it's got to be A. Okay, here's the issue. This is an equivalent form of that quadratic equation. Okay, it's the factored form. And you can actually see that the zeros are x equals 5 and x equals -3. But that's not what they wanted. You can see what the zeros are, or the x-intercepts they're called, in this equation as constants, but they didn't want that. They wanted the coordinates of the vertex as constants. So I'm going to sort of rewind here and get rid of all that just so it's not too misleading. But that's the major pitfall, the major bait answer that you're seeing in here. Okay, so if you notice the coordinates of vertex A, way down here, if you look, it's just below the 15, and it's perfectly on the 1, right? So I would say the vertex would be 1, -16. And which one of these contains that? It's D, because this is in vertex form. And just remember, vertex form, it's called vertex form because you can see the coordinates of the vertex in the equation itself. So in this case, the vertex is H, K. And they wanted the form of the equation that would allow us to see the coordinates of the vertex actually in there. Okay, so just watch out for what they're asking because, like I said, you know, this is what you get if you factor it. And there have been questions in the past. It's on a test that's no longer in this edition of the book, but there was another problem that asked for a version of this. It was in standard form like this, where the zeros or the x-intercepts would be visible as constants. And in that case, this would have been your guy, okay? But not so for this one, because we wanted the vertex. 31 is the first of the grid-in problems on the calculator section here, and remember that the difficulty resets once the grid-in starts. So 31 is actually an easy, don't overthink this too much, right? So they want to know a possible amount of time it would take for Wyatt to husk 72 dozen ears of corn. Don't get too caught up on the dozens here. They're just sort of there to confuse you. Just think of them as like single units, like 72. How long does it take him to do 72? And in terms of his rate, he does somewhere between 12 and 18. So if he goes as fast as possible, he would be doing 72 dozen divided by 18 dozen ears of corn per hour, right? So if you divide this out, this would be 4 hours. Now, if he works as slow as possible, 72 dozen divided by 12 per hour, and that would give you 6 hours. So he would produce, the time it would take him is somewhere in between 4 and 6 hours inclusive. So they say, what is a possible amount of time? Anything in between 4 and 6, inclusive of 4 and 6, would work here. 32 isn't too bad as long as you read it carefully and just sort of visualize what's happening. Don't overthink it, right? We've got a weight limit on a bridge that's 6,000 pounds, right? And then we've got a delivery truck that's carrying X identical boxes, each weighing 14 pounds. And then the combined weight of the empty delivery truck and its driver is 4,500 pounds, okay? So what you want to understand here is that basically the truck itself is 4,500, right? And then we've got X identical boxes that are 14 pounds each. So how would you code that algebraically to account for the weight of the boxes, that would just be 14x. So we've basically got truck and driver, but just think about it as a truck, right? Plus the boxes has to stay under the weight limit of 6,000 pounds. So it's good to be comfortable with inequalities here, coding them just like equations, because it just makes you more confident in some of the answers that you'll get in certain grid-in problems especially, okay? So don't be shy about using inequalities instead of equations, but like this amount has to be less than or equal to the bridge's max, weight capacity, so 6,000. And then you just solve it algebraically, right? So I'll just write it out here so I can have some room, but just subtract your 4,500, and then you'll end up with 1,500 on the right, and then you'll just end up dividing both sides by 14. And remember that x represents a number of boxes, okay? So when you divide this out and you get 107.14, that's not really a possible number of boxes. This is a discrete measurement, it's called, where you can only have whole numbers of boxes, right? So what is the maximum possible value for x, or max number of boxes? That would be 107 to stay under that weight limit. For 33, there's a really nice percent building trick or fraction building trick that you can use called the is of trick. So when building a fraction or a percent, is will go on top and of will go on bottom. So the number that's paired next to the is will go on top, and the number paired next to the of will go on the bottom. So if you look at here, it's saying sold in 2008 is what fraction of the number sold in 2011. So this is going to be, since 2008 is paired with the is, it's going to be like the 2008 number over the 2011 number, because 2011 is paired with of. So 2008 over 2011. So let's look up at 2008. That is 100. And then 2011, that's going to be 160. And then remember, a nice way to reduce fractions that end, with numbers that end in 0 on the top and bottom here is dividing by 10 will get you the same thing as slashing these zeros, like a pair of zeros. And if there are multiple zeros, you could slash multiple, right? But yeah, just a nice quick way to reduce. So this comes down to 10/16, and then just reduce those by 2, and you end up with 5/8. 34 is kind of basic, but you just have to visualize it properly, right? So the time slots are in 30-minute intervals, and then it's saying it operates 24 hours per day, every day of the week, so it's going all the time. How many 30-minute time slots are there on Tuesday and Wednesday, essentially? So if you just go with like Tuesday, I would turn this into hours. I think that's probably the easiest way to think about it, right? So like 30 minutes times 2 would make 1 hour, and then times 24, right? So that would be, let me just write it like this. That would be 48 slots on Tuesday, right? And then for Wednesday, that would be another 48 slots. So you just add them and you get 96 total. 35 looks a lot worse than it is, but really it just involves the volume formulas for a cylinder. And what I see happen most often with students here is they forget that the volume formula for cylinders is actually listed at the beginning of every section in the book. So I'm just going to sort of bring this up real quick so you can see. If you go back to the very beginning of the calculator math section and the no calc, it's listed in the no calc too, you've got all these formulas, right? So don't forget that these are here. So here's our one for cylinders here, like volume equals pi r squared h. Also, keep in mind that they give you these two guys. This one in particular is good for radians, for pre-calc based problems. If you haven't taken pre-calc, that's really useful to know, okay? So going back here, the volume formula is just pi r squared times the height. And since they give you the volume, you can just pop it in right there, and you'll end up just solving for the radius. Now, as a general bit of advice for this test, you never want to multiply pi out as like 3.14 or anything like that. Almost all answers involving pi will be expressed in terms of pi. So at like A, B, and C would be like 20 pi, 30 pi, 40 pi, whatever. They're not going to have you multiply it out and actually have turned it into a decimal to do, your calculations with, okay? Just because most of the time it's going to cancel out, as you're going to see here. Also, I didn't plug in our height. This is our height. It's 8, right? So I'm just going to sort of plug that in here. So it's like times 8. And if you look, you can divide both sides by pi right away. And it's going to cancel here and here. So 72 equals 8r squared. Divide that out by 8. And you end up with r squared equals 9. Square root both sides there. And r equals 3. Be really careful here. It's a really good lesson in double checking what they're asking for. They want the diameter. Okay, a lot of people will list the radius as their answer, but remember, in a circle, this is the radius, this is the diameter. So the whole thing, whole way across the circle going through the center is the diameter. It's just double the radius, so the diameter is 6, and that's it. 36 is kind of a good exercise in foiling and factoring and also just remembering what undefined means, right? So they're asking what value of x makes the function h undefined. Undefined is when you divide by 0. Remember, dividing by 0 isn't possible because you can't cut something into 0 pieces. So this is what produces the undefined result versus this. Like if you have 0 pencils, let's say, and divvy them up amongst 4 students, like how many pencils per kid is that? It's 0, right? Because you had 0 to begin with, divvy that up, your amount per kid is still 0, right? Versus up here where this is like 4 pencils divvied up amongst 0 kids. So how many pencils per kid is that? Well, you don't even have kids to start with, so that doesn't make sense. That's just the way I like to remember it, not the way I like to explain it. But in any case, having 0 in the denominator is what produces the undefined result. So if you look at this whole denominator is what cannot equal 0. So what you're going to do is set it equal to 0 to see what value of x would cause the denominator to be 0. So easiest way to go about this, there is a shortcut which I'll explain a little later, which is just, I don't know, kind of for the lols, but you just FOIL this out and then distribute this guy. So that's going to make 4x minus 20. And then foiling this. Right? Remember, you have to FOIL a situation like this. You can't distribute a square in. That's one of the biggest mistakes, one of the most common mistakes related to foiling. Okay, you do have to FOIL this out. So x squared minus 10x. Well, let me show my work there. Minus 5x, and then plus 25. And then if we just combine some like terms over here, it's like plus 4x, and then this will make negative 16. And then combine those along with that. So x squared minus 10x plus 4x is minus 6x. And then the 25 minus 16 makes positive 9. And then this can be factored. So again, with factoring, you're looking at the last number first, thinking about what multiplies to get that number. So we got like 1 and 9, 3 and 3. And then you're choosing the factor pair that could possibly add or subtract to get this number. And that's 3 and 3. At this point, you want to think about the signs that go on those 3's to make negative 6 when you add them. So that's just negative 3 and negative 3. So you could either condense that into x minus 3 squared and solve from there, or just skip that and realize that you're just going to get 3 from both of these. So 3 is what would cause the entire denominator to be 0. So it is 3. Okay. Now, real quick with the, let's see, I'm going to write this answer over here. There we go. The weird shortcut that I have to believe they put in here deliberately, just because it works out too well. I'll show you right now. Sometimes there are these little Easter eggs for nerds in this test, I swear. But basically, see how these, I'm going to use some green, see how the x minus 5's match? This has the structure of, like, if you let a equal x minus 5, I'm going to rewrite this now with a plugged in, it would be like 1 over a squared plus 4a plus 4, right? And then if you factor that, that's 1 over a plus 2, a plus 2, or 1 over a plus 2 squared. And then if you replace the a with the x minus 5, pop it in there, you get 1 over x minus 5 plus 2 squared, which is 1 over x minus 3 squared, which is the exact same thing we got over here. So that's just 3 for what would cause that to be undefined. So yeah, fun little factoring thing there. 37 is pretty important because it technically deals with exponential growth and decay, which is a pretty prevalent concept on the SAT. So what I'm going to do is, in order to save time, I'm just going to bring up a lecture that I created on exponential growth and decay. And by lecture, I just mean it's sort of like a little pictograph, explanation. You'll see here. But I created it with a student, so you have to pardon the word problem example. I let her pick the animal that we would want a lot of, okay? So she ended up choosing lemurs, which, I totally understand as a choice, believe it or not. I think the world would do better with more lemurs. So here we are. If we look at this, okay, I'm just going to sort of walk us through this. The exponential growth and decay word problem structure that you'll want to default to is this up here, and hopefully you guys can see that pretty well. But basically, your final amount A will equal the initial amount P. You guys probably remember this if you took Algebra 2. And then it's 1 plus or minus the rate of increase or decrease, but with that percent written as a decimal. So like, let's say you're gaining 50%, the R would be 0.5, and you would add that in that case. Whereas if you're losing 50%, again, the R would be 0.5, but you'd be subtracting it, right? And then T is just time. So what you'll end up doing, as you'll see in the word problems below, is you will end up plugging this information into here, and then it's going to boil down to having the structure of y equals a times b to the x. It'll be sort of more simplified looking that way. So if you look at a growth situation, that's any time this b value with the exponent on it ends up being greater than 1. So for example, start with 200 lemurs, pretty good situation, right? And gain 50% per year. So the final amount would equal 200, that's the p principle, right? And then 1 plus 0.5 because we're gaining 50% per year. So you end up with 1 plus 0.5, which is 1.5, and then 200 times 1.5 to the x. I've got a nice little table of values here. At year 0, we've got 200, and then 50% of 200 is 100. So you can see that we're gaining that 100, and now we're up to 300 after 1 year. And then 50% of this amount, the 300, is 150. So if you add that on, we end up at 450 for the second year. And you end up with this nice exponential growth curve that you're seeing here, okay? So that's what you want to associate with exponential growth anytime this number ends up being greater than 1. Now, on the other hand, if you start with 200 lemurs and lose 50% per year, sad, it would be 1 minus 0.5. And then the decimal, the b value, ends up being in between 0 and 1, which is what this is saying. So that creates a decay situation, and now you have every year the amount is taking 50% of itself. So starting at 200 once again, here's our little y-intercepted 200 here, and then half of 200 is 100, and we're losing that amount. And then half of 100 is 50, and we're losing that amount. So this little progression makes sense, and this is what's called an exponential decay curve as you go through like that, right? Now, this problem is dealing with exactly this, and you can actually see the y equals a times b to the x structure in here, okay? Just the variables are a little jumbled up and we don't have a y equals, but you can sort of imagine it there, right? And you can see that the x that they're looking for is actually the b value, and the way you get the b value is by doing 1 plus or minus r. So it's saying she starts with $100, so that's the principal automatically. Let me actually use the a equals equation. So it'd be like a equals 100, and then when we do plus or minus, and she's earning 2%, so definitely plus, and make sure you use the decimal value of 2%. So the decimal's currently here, move it to the left 2 places, you end up with 0.02. So it is 0.02 as a decimal, so 1 plus 0.02 to the t. Combine these guys, and you end up with this. And then the 1.02 is the x value that they were looking for. So that's it. Okay, for number 38, I'm going to be going through this kind of quickly. If you have any trouble with how I'm getting my expressions for how much Jessica and Tyshawn make after 10 years, just head back to my lecture for number 37, because that explains the exponential growth and decay setup and how you get the expressions and what goes where and all that kind of stuff. So if you got 37 or you're understood 37, you should be totally fine with this. If not, go back, look at 37. Okay, I have a nice little drawing, pictograph thing that I use to explain everything. So with that said, Jessica's amount should be, since she puts in 100 and then gains 2% every year, this is how much she makes after 10 years, right? And then Tyshawn puts the same amount of money in, but 2.5% expressed as a decimal, if you go back 2 places, that's 0.025. So it's 1.025 to the 10th. This would be his final amount after 10 years. So if you do this out here, you get 121.899 for Jessica. For Tyshawn, you get 128.008. And I'm going to 3 digits because it's going to show how important the rounding is here. Because if you don't get this answer dead on, you just get it wrong, okay? So notice how they say round your answer to the nearest cent. Watch out for the rounding rules, in particular on numbers 37 and 38 in the calculator math sections. They just love to put very specific rounding rules, like sometimes it'll be to the nearest dollar, just arbitrarily, right? But if you don't follow their rounding rules exactly, you will get this wrong, okay? So knowing that we're going to the nearest cent, when we get our individual amounts here, we need to round to the nearest cent, which would be to this place value and this place value. So to see how that rounds, we'll look to the next digit. The 9 will round this 9 up, so 89 becomes a 90. So it's like 121.90, and then looking at the 8 to see what happens to the 0, that's going to round up as well. So 128.01, and then off to the side, how much more did Tyshawn make? Just subtract them, and again, you can see if you didn't do the rounding correctly and you just looked too quickly, you would have gotten this wrong. So be careful about the rounding. 6.11 is your answer. Not too shabby as long as you follow your rounding rules.
For those of you interested in more in-depth videos and online one-on-one tutoring, head over to capstoneacademics.com and reach out to us through the Contact Us form, email us, or call us. The link's in the description below. For free walkthroughs, test-taking tips, and updates, follow us on social media on YouTube, Twitter, Facebook, and Instagram. Thanks so much for watching, guys. If you found this helpful, please go ahead and hit the like button and subscribe for more SAT walkthroughs and math help all year long. This is Jesse Brockwell from Capstone Academics. Thanks so much for watching, and see you soon.